All right. Let's go. Let's check the audio. Whoa. It looks good. Let's set up the iPhone externally. Where is so my video? Okay, let's check the audio. Okay, sounds okay. Sounds okay. So let's look into this thing called Bell's inequality, Bell's theorem. What is going on? 1 second, I have an email. What is this email? Okay. How do I transfer this? Maybe I can print it. Once I print it, I guess I have to save it to PDF. Okay, whatever. Forget it. Let me just do it from the iPhone. So share with the team. Okay. Let's check that it's been transferred properly. Okay, very nice. Who is in this team? That's good. Good. All right, we're done. Next topic of the day. All right, so Bell's inequality. What is Bell's inequality? AC off. All right, what is going on? So Bell's theorem. Okay, let's look for Bell's theorem.
Just go ahead and hit the main points. First, photons.
Okay, so I was listening to these guys. Okay, let's
just go ahead and hit the main points.
Let's try this.
They would be black, which puts them in a subset of this other.
If you have polarized sunglasses, you have a quantum measurement
So this is Henry, probably.
device.
Each of these pieces of glass is what's called a polarizing filter, which means when a photon of light reaches the glass, it either passes through or it doesn't. And whether or not it passes through is effectively a measurement of whether or not that photon is polarized in a given direction.
Try this. Find yourself several sets of polarized sunglasses or old photographic filters. Look through one set of sunglasses at some light source.
Graphic filters. I don't know what those are. Okay.
Like a lamp. Then hold a second polarizing filter between you and the light. As you rotate that second filter, the lamp will look.
You know what? I saw a video.
Just go ahead and hit the. Just go ahead and hit the main.
I have a message. Let me get the message. All right. So quantum entanglement, Bell's inequality from 8 years ago. This is maybe preferable. EPR paradox.
Quantum entanglement is one of the most mysterious phenomena in existence. Quantum entanglement.
She from. Oh, 1 second. Let me. All right. Okay, are we back in business? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. Okay, so we're good. We're back in business. All right. All right. Okay, so let's check this video out.
Entanglement seems to indicate that messages can be sent from one particle to another instantaneously, even if the two particles are located on opposite sides of the universe. However, according to Einstein's theory of relativity, no information can ever travel faster than the speed of light. According
No, this is not according to Einstein. This was actually, I would say, probably if when they assumed the ether, they would have assumed just the same. They didn't know if there's anything else that moves faster than light. Einstein doesn't know any better. There's no reason to assume that Einstein discovered this law. Nothing is known to travel faster than light, and the speed of light is a constant. They should stop saying this is based on Einstein's relativity. It's not. It's just the facts. That's what we know. Not because of Einstein's theory. It's empirical knowledge. Nothing has been shown to be able to move faster than light. That's all.
to Einstein's theory of relativity, if a message could travel faster than the speed of light,
Second, I need to listen to a message.
then it would be possible to send messages backwards in time. Yet, quantum messages traveling instantaneously can seem to be demonstrated by measuring the polarization.
Yeah, it's nonsensical. If something can move faster than light, then it violates causality. That's ridiculous.
Of two entangled photons, or by measuring the spins of two entangled particles, such as an electron and a positron. The principle for quantum entanglement is the same in both cases, but in this video, we will just focus on measuring the spins of particles such as electrons and positrons. and the polarization of photons will be discussed in a separate video. In classical physics, the spin of a particle can be represented by an arrow pointing along the axis of rotation. Particles spinning in opposite directions have their arrows pointed in opposite directions. We have the ability to measure the spin of the particles with a detector. But in quantum physics, the detectors always provide us with only one of two measurements, which is either towards the red plate or towards the blue plate. Therefore, depending on how we orient the detectors, we can measure the spin in only one direction at a time. We have the ability to produce pairs of particles, which we refer to as an entangled pair. We can measure each of these particles with a separate detector. If we align the two detectors in the same direction, then the spins of the two particles will always be in the opposite directions 100% of the time. This is predicted by both classical physics and by quantum mechanics.
That's good. As long as it's predicted by classical, then I'm happy.
If the two detectors are aligned 90 degrees to each other, the two particles measure opposite spins exactly 50% of the time. This is also predicted by both classical physics and by quantum mechanics. But if the two detectors are aligned somewhere in between these two directions, then quantum mechanics gives a very different prediction than does classical physics. According to classical physics, the angle of the two detectors should have a linear relationship to what percentage of time the two particles have spins in opposite directions.
Let's see. So if it's 0, then it's opposite. If it's 90 degrees to each other, then it's 50% of the time. 180 degrees from each other, it's complete correlation. That's classic, okay.
But according to quantum mechanics, this relationship is a sine wave.
What? Why? Why is it different? So they're not going to explain why it's a sine wave?
When we actually perform the experiment, the result we get is always the one predicted by quantum mechanics, and not the one predicted by classical physics. Suppose we align the two detectors 45 degrees to each other. Classical physics predicts that the two particles should have opposite spins 75% of the time.
Oh, at 45 degrees, %. Why? Because 90 degrees is 50%. At 180 degrees, it's completely correlated. 0 is completely opposite. 90, 50%. Why should it be different, classic versus quantum?
But quantum mechanics predicts that the two particles should have opposite spins approximately 85% of the time.
Isn't this the cosine squared? If they are opposite, if it's 0 degrees, then we expect perfect opposites. If it's 90 degrees, we still expect 50%. If it's 180 degrees, we expect complete correlation. I don't get it. Why should it be different?
And it is this 85% which is actually measured. However, the fact that we measure 85% instead of 75% implies an inherent logical contradiction, leading us to believe that the two particles are sending messages to each other instantaneously, with all the inherent implications about messages traveling backwards in time. In order to understand why this is the case, let us first consider a simple logical thought experiment that is not related to quantum mechanics or to this experiment with the measurement of spins. Suppose we have a collection of marbles. Each marble has three properties that we will call X, Y, and D. For each marble, we are allowed to choose only one of these three properties to measure. Each of these properties can have only one of two values, which we will call.
Why is it so complicated to explain something so trivial? What's the difference between classical and quantum?
Red and blue. That is, the X property of each marble can be either red or blue. The Y property of each marble can be either red or blue. And the D property of each marble can be either red or blue. Suppose that all the marbles are arranged in groups of two. That is, each marble is partnered with one other marble. Each marble is separated from its partner, and the two marbles are placed on opposite sides of the universe. We now choose one of the three properties to measure for each of the marbles. If we choose the same property to measure for both a marble and its partner, then we always get the same outcome for the two marbles. That is, the X property of the two marbles either both come out red or they both come out blue.
Why?
The Y property of the two marbles either both come out red or they both come out blue.
And the
D property of the two marbles either both come out red
or both blue.
or they come out blue.
Why? Who determines that?
Now suppose we choose different properties to measure for a particle and its partner. If we measure the D property of one of the marbles, and we measure the X property of its partner, they both always have the same value. And if we measure the D property of one of the marbles, and we measure the Y property of its partner, they again both always have the same value.
Why?
Now, what if we measure the X property of one of the marbles, and we measure the Y property of its partner?
What is going on?
Based on the information presented so far, we should expect that they too should always have the same result. What if we were told that this is not the case, and that they have the same value only 50% of the time? This would seem to be a logical contradiction with the information we have been presented. If D is always the same value as both X and Y, then X and Y must always be the same value as each other. But what if when we actually performed the experiment, X and Y were in fact equal to each other only for 50% of the pairs of particles? This would imply that there is something fundamentally wrong with the rules of logic as we understand them.
What is going on? I don't understand.
Now let us consider a slightly different scenario. Again, suppose that we have a collection of marbles, and each marble is again partnered with one other marble as described previously. As before, each marble has three properties, which we will call X, Y, and D, and it is possible to select only one of these three parameters to measure for each marble. As before, if we choose the same property to measure for both the marble and its partner, then we always get the same outcome for the two marbles 100% of the time. But this time, if we measure the D property of one of the marbles, and we measure one of the two other properties of its partner, they have the same measurement 85% of the time.
Oh my god.
That is,
What?
if one of the marbles has red for its D parameter, then its partner has red for its X parameter 85% of the time.
Don't tell me anyone understands this. This is the most convoluted video. I don't know what's going on. This is a terrible video. Sorry. Okay, listen to this guy. Very difficult to understand. Okay, let's try this guy.
So forth. But the weirdness, the spookiness is that they're in a fuzzy mixture, and yet upon measurement, they both disambiguate. They both choose a definite reality. Even though they're far apart, they're able to correlate the outcomes. That's the weirdness. So far apart, and yet they never get it wrong. When one's up, the other's down. When one's down, the other is up. Amazing, right? So what does Einstein say to this? He says, look, he says, that's too damn spooky for me. He says, I think what's really going on here is not that these particles are in this fuzzy mixture of up and down until they get to the detectors, and only upon measurement do they snap out to be one way or the other. He says that would require some spooky crosstalk between them, some spooky
I agree with Einstein.
conversation between these widely separated particles. He says the world doesn't work that way. So he says,
Sometimes I agree with Einstein, sometimes I don't. He doesn't always get things right, but in this case, he's absolutely, it's absolutely critical that we believe him. Otherwise, nothing makes any sense. This is too fundamental to just ignore.
I have got a much simpler explanation for what's really going on here. He says, if a detector measures a particle and finds it spinning up, then it always was spinning up. It was never in this fuzzy mixture spinning up and down, as the math of quantum mechanics tells us.
That's good.
He says the math of quantum mechanics is simply unable to get at the full and complete description of reality. And that's why it seems to us, by staring at the equations, that a particle is in a fuzzy mixture of up and down until measurement, when in reality it always was up or down from the get-go. And
I don't know what you're talking about, the math. The math is just the data. The math is just the conclusion of the data. I'm just going to ignore the word math. So, okay.
then to explain how when this one's down, this one's up, very simply. This was always down and this was always up. And that's how they were from the get-go. And these detectors simply revealed the definite spin that they already had. So pictorially be like this. We have here the spins of the particles coming out, and they're definite from the get-go, according to Einstein, Podolsky, and Rosen. The one on the right, at least my right, is spinning up. The one on the left is spinning down. And that's all there is to it. So of course, as they race toward their two detectors, they maintain those spins, and the detectors reveal those spins. So Einstein says, here is what's...
What do you mean the one on your left, the one on your right? How could it be different than ours? We're watching a video. You're not watching something from the other side of the room. There is no room. It's a video simulation.
really going on. Particles have definite properties, even though quantum mechanics can't give us those definite properties. Quantum mechanics only gives us probabilities of those definite properties, but definite properties that particles have, and they're opposite to each other on the left and the right, and therefore it's no surprise that the measurements always yield this perfect anti-correlation. One is up, the other's down, one's down, and the other is up. Nothing spooky at all in this Einsteinian, Podolskyan, Rosian description of the true underlying reality. So this is what the New York Times meant when they said that Einstein, Podolsky, and Rosen were not saying that quantum mechanics is wrong. They're saying it's incomplete. They're saying that, sure, the predictions of quantum mechanics, spot on accurate, but the true picture of reality that underlies the mathematical description is quite different, they are claiming, from the reality that's manifest in the quantum mechanical mathematics. According to quantum mechanics, particles can be in this mixture, and then measured, they snap out of the haze. Einstein says, no. They always had a definite spin. It's just that your incomplete quantum mathematics is unable to tell us that definite disposition. And because your theory is incomplete, it's reduced to giving probabilistic descriptions of a reality, but that's only a description. That's not how reality actually works. Now, when Einstein came forward with this idea, there was definitely some, how should I say it? Well, there was concern, that Einstein maybe was pointing out a failing of quantum mechanics. Maybe Einstein was right, but then people began to think about it more fully. And they began to realize, or at least they began to think that they realized, that Einstein's view of reality could never be tested, fundamentally couldn't be tested, right? I mean, this guy over here, Wolfgang Pauli, he said that Einstein, Podolsky, Rosen's view of reality was no better than the ancient question of how many angels can dance on the head of a pin. It was something that was untestable. Now, why would it be untestable? Well, you see, Einstein is saying that before you measure the particle, it has a definite spin, whereas quantum mechanics says it's in a mixture, right? But how do you verify that picture without measuring the particle? The only way you can learn the disposition of the particle is by measuring it, but after measurement, Einstein agrees that it will have a definite value, say up or down, and quantum mechanics agrees that it will have a definite value up or down. They only differ. These two views of reality only differ from each other prior to the measurement. How can you ever test something that's prior to the measurement? It's as if I said to you, hey guys, did you know that I actually have pink hair, but anytime you look at me, my hair turns white or gray or whatever color my hair is, right? My statement that I have pink hair when you're not looking is fundamentally untestable because the test that you need to look, but I'm stipulating that when you look, my hair is no longer pink. So Pauli makes the analogy to angels dancing on the head of a pin. And Niels Bohr, who was Einstein's, deep partner in trying to understand the fundamental laws of physics, Bohr's view was, he said, look, it is a mistake to think that we physicists are in the business of trying to find the true nature of reality. Nonsense, Bohr says. We are in the business of trying to find the equation that will make accurate predictions for the results of measurements. And if you try to think that we physicists are doing anything more than that, you're going to run into problems. And that, he says, Niels Bohr, who was Einstein's, deep partner in trying to understand the fundamental laws of physics.
He was Swiss, half Jewish, anti-Nazi, like Einstein. He hated the Nazis.
Bohr's view was, he said, look, it is a mistake to think that we physicists are in the business of trying to find the true nature of reality. Nonsense, Bohr says. We are in the business of trying to find the equation that will make accurate predictions for the results of measurements.
No. That's not science. That's nonsense. No, you have to understand reality or you're irrelevant.
He said, look, it is a mistake to think that we physicists are in the business of trying to find the true nature of reality.
It's ridiculous. That is science. Science is trying to explain reality.
Nonsense, Bohr says. We are in the business of trying to find the equation that will make accurate predictions for the results of measurements. And if you try to...
No, you have to come up with a mechanical explanation of any phenomenon. That's your job.
Think that we physicists are doing anything more than that, you're going to run into problems. And that, he says, is what Einstein has run into. He basically says, in the end, if there's no experimental difference between the Einsteinian view of the underlying reality and the quantum mechanical view of the underlying reality, then we're not talking physics any longer. So Einstein passes away in 1955. Bohr passes away in 1962. And this issue of what the true nature of the world is the world in a fuzzy probabilistic haze until measured or until there's a suitable interaction? Or is the world actually definite and your measurements just reveal that definite reality? Which of those pictures is correct? People basically don't pay a lot of attention to the issue for a period of time because I think it's fundamentally untestable, fundamentally not physics, fundamentally perhaps philosophy. I don't mean that in a derogatory way. I mean more of a philosophical view of how the world is as opposed to a physicist view of the things that we can measure in the world. And that's where this guy I mentioned early on in this episode, John Stuart Bell, comes into the story. Because in 1964, he writes a paper. I'll show you that paper in just a moment. He writes a paper that shows the Einstein view of reality is testable. Pauli was wrong. It's not about angels dancing on the head of a pin. Bell surprisingly shows that Einstein's view of a world in which qualities are always definite, that yields a measurable difference, an experimentally distinct prediction from the quantum mechanical prediction. How does he do this? Well, I'm going to focus on the little example that we've been looking at, particle spin. I mean, the paper that Bell writes is much more general than that, but let's just try to get at the heart of the matter. What is the essential new idea that Bell introduces? He says, look, let me just imagine doing that laboratory experiment with the spinning particles with the two detectors on opposite ends of the laboratory bench. But let me imagine that I went to the physics supply store and I got some better detectors, upgraded detectors. Imagine that the detectors don't just measure the spin along one axis, the vertical axis that we were looking at. Imagine that it can measure the particle spin about three different axes, axis 1, axis 2, and axis 3. Now, exactly what those axes are does matter to the mathematical version of the argument that I'm about to give you. You don't really need to know that because I'm going to focus sort of at a higher level. We will do the mathematical analysis, but we won't get into that level of detail. But just in case you're interested, the three axes that Bell envisions are axes that are at 120 degrees relative to one another. So, this axis, that axis, like a peace sign, that axis, and this axis. And so what this detector does is when the particle comes in, you, the user, the experimenter, pick one of the three axes while the particle is, say, in flight. You pick axis 1 or 2 or 3, and the outcome will be the measurement of the particle spin along that axis. Now, the weirdness of bread and butter quantum mechanics that nobody's questioning is that the result of that measurement will always be spin up or spin down along that axis. Now, I'm not going to distinguish in the readout the different orientations. I'll always show up or down, but you take it to mean that it's up or down along axis 1 if I pick one, up and down along axis 2 if I pick setting 2 on the detector, similarly up or down along axis 3 if I choose setting number 3. And again, just so it's clear, here's Bell's paper, which I can just thumb through it again. It's not long, and you see that there's more general mathematical analysis that you see in this. But
This is already a problem. To tell me that it's always that the result will be along the direction of the measurement with a certain probability. This already you have to be able to explain. How does that happen? So it's incoming randomly, then it should be explained classically. Why is there a difference between classical and quantum behaviors? It comes in randomly, you test it. Right? Imagine you have a coin flipping, right? That you can only tell is it up or down. There's no angle to a coin. It's either up or down. Coin. You flip it, it's either up or down. So it's going to be 50% of the time, obviously. But what if you could tilt the surface? That should not give you a different answer. So it's not a good idea. So let's start over. So let's say you have some random angle generator. That's also not good. But let's say you can only get the dot product with the angle that you're measuring. No. What is a classical? Why is this the case? So let's say you have a spin, an electron spinning, and you measure the spin, or even with a photon, you measure the polarity. For some reason, it's always, the polarity is always in accordance with your measurement a certain percent of the time. So in quantum mechanics, because of the all or nothing of the particle. Anytime you interact with the particle, this is weird. I mean, the problem is with entanglement. It's a problem.
It's nothing more than basic quantum mechanics, linear algebra on this right-hand page toward the bottom, a little bit of calculus, but that's it, right? That's the end of this paper, which gives us, in the end, as we'll see, a shocking insight, shocking conclusion. But the version of understanding this at a pedagogical level that I will follow, following this example of the particle spins, I learned from this guy over here, David Mermin. I was a professor at Cornell in the 1990s. David Mermin has been at Cornell for a very long time. I think maybe retired now. And he just has this spectacular knack for drilling down and really finding the heart of an argument. And I remember I went to a colloquium at Cornell where David Mermin was explaining Bell's ideas. And I sort of heard of Bell's ideas at that time. I was a faculty member at that time. I sort of knew about Bell's ideas. I didn't really know about Bell's ideas. And after this colloquium with David Mermin's, I was just like walking around in kind of state of shock when I finally understood in an intuitive way that I will explain right now what John Bell was telling us. Okay, so let me show you then how the argument goes in this particular version that David Mermin gives us. So here's our detector. We can choose axis 1, axis 2, axis 3, and each of these detectors are in this configuration. And now I should say, when a particle pair is emitted by this particle creation in the center there, it sends the particles out left and right. Now the particles have to have definite spins along all three of the possible axes, according to Albert Einstein. Einstein says, again, particles have definite features. When you measure something that's already there. So if we're measuring the particle spins along axis 1, then the particle better have a definite value to spin along axis 1. And you see it right here. The left particle is spinning up along axis 1, and the right, again, they're completely anti-correlated. That's the nature of this entangled state. But you see particle 1, particle on the left along the first axis is spinning up. Particle number 2 along the first axis is spinning down. Similarly, the particle on my left along the second axis, you got the purple.
This is so confusing. There's what's going on with all these arrows? So 2 here, the 2 side ones are up, the center is down, which is purple. Here the 2 purples are down, the directions are the opposite. What is going on with I don't know what's going on here.
Pointing down, the corresponding measurement on its partner, entangled partner particle on the right, the middle arrow is spinning up. And finally, you see that the third arrow on the left particle spinning up. The third arrow on the right is...
Let's check it.
spinning down. So according to Einstein and colleagues, this is the true nature of the underlying reality. It's none of this business along these axes. And now the explanation for the results in this view of reality would be completely clear. So let's imagine we run some experiments. Let's say we pick axis 1 for the detector on the left and the right. That means the first arrow for each of the entangled particles.
Okay, there's 2 people watching. Wait, let me give you the link if you want to join. Let's see. Okay.
Dictates the outcome, and you see the one on the left is spinning up and the one on the right is spinning down. Now, if I pick the second axis for both of these, it's the second arrow in the triples that matter. So you get spinning down on the left, spinning up on the right. And for good measure, let's set the detector to be axis 3, and it's the third arrows of each of these triplets that matters, spinning up on the left, spinning down on the right. And the detectors simply reveal the underlying quality of the particle that Einstein and his colleagues.
I have no idea what this is, what's going on here with this experiment.
In the 90s, David Mermin has been at Cornell for a very long time. I think he may be retired now. And he just has this spectacular knack for drilling down and really finding the heart of an argument. And I remember I went to a colloquium at Cornell where David Mermin was explaining Bell's ideas. And I sort of heard of Bell's ideas at that time. I was a faculty member at that time. I sort of knew about Bell's ideas. I didn't really know about Bell's ideas. And after this colloquium with David Mermin's, I was just like walking around in kind of state of shock when I finally understood in an intuitive way that I will explain right now what John Bell was telling us. Okay, so let me show you then how the argument goes in this particular version that David Mermin gives us. So here's our detector. We can choose axis 1, axis 2, axis 3, and each of these detectors are in.
I don't know. Why do you need such a complicated discussion? I mean, I'm already having a hard time. Once you assume entanglement and that revealing one reveals the other. So Einstein said, yeah, they were preset. There's hidden variables, whatever. So Einstein resolves it. But Bell says that's impossible. So, okay, what are we testing here? We're testing 3.
This configuration. And now I should say, when a particle pair is emitted by this particle creation in the center there, it sends the particles out left and right. Now the particle.
So it's a really weird particle that's created. That's composed of 3. So the left one has 2 up. The right one has 2 down. Oh, they're just opposite each other. Is this the point? They're opposite each other? Everything is opposite? The up is always orange, the down is always purple. And they're just opposite. So the left, 2 up, 1 down. 2 outer ones are up, center one is down. And the right is center one is up, side ones are down. So everything is opposite. Okay.
Particles have to have definite spins along all 3 of the possible axes, according to Albert Einstein. Einstein says, again, particles have definite features. When you measure something that's already there. So if we're measuring the particle spins along axis 1, then the particle better have a definite value to spin along axis 1. And you see it right here. The left particle is spinning up along axis 1, and the right, again, they're completely anti-correlated. That's the nature of this entangled state. But you see particle 1, particle on the left along the first axis is spinning up. Particle number 2 along the first axis is spinning down. Similarly, the particle on my left, along the second axis, you got the purple pointing down. The corresponding measurement on its partner, entangled partner particle on the right, the middle arrow is spinning up. And finally, you see that the third arrow on the left particle spinning up, the third arrow on the right is spinning down. So according to Einstein and colleagues, this is the true nature of the underlying reality. It's none of this business along these axes. And now the explanation for the results in this view of reality would be completely clear. So let's imagine we run some experiments. Let's say we pick axis 1 for the detector on the left and the right. That means the first arrow for each of the entangled particles dictates the outcome. And you see the one on the left is spinning up and the one on the right is.
We're testing 1. We're testing the leftmost. Before, I think this was an intermediate step. Okay, so we're testing 3. The left is up, the right is
The
down.
explanation for the results in this view of reality would be completely clear. So let's imagine we run some experiments. Let's say we pick axis 1 for the detector on the left and the right. That means the first arrow for each of the entangled particles.
Wait, what?
True nature
We
of the
never,
particles
so we
spinning up.
never
The third
tested.
arrow
So we never tested this state.
on the right is spinning down. So according to Einstein and colleagues, this is the true nature of the underlying reality. It's none of this business
So left is up, right is down.
along these axes. And now the explanation for the results in this view of reality would be completely clear. So let's imagine we run some experiments. Let's say we pick axis 1 for the detector on the left and the right. That means the first arrow for each of the entangled particles dictates the outcome. And you see,
I didn't want that to happen.
we run some experiments. Let's say we
This is
pick
3.
axis 1 for the detector on the left and the right.
Okay, this is 1. Has it already been said? I don't know. So the left is up and the right is down.
That means the first arrow for each of the entangled particles dictates the outcome. And you see the one on the left is spinning up and the one on the right is spinning down. Now, if I pick the second axis for both of these, it's the second
Second axis. So left is down, right is
arrow
up.
in the triples that matter. So you get spinning down on the left, spinning up on the right. And for good measure, let's set the detector to be axis 3, and it's the third arrows of each of these triplets that matter.
Oh my God. Give me a minute, a minute, a minute, a minute. I wish I could freeze the recording. Freeze the what's the method by which to freeze the recording? Forgot. How does one freeze the recording? Setting hotkeys. And pause P. So just P. Let's try P. Error occurred. Wait a moment, then try again. It doesn't freeze. It doesn't work. How difficult can it be to freeze a recording? Really sad, really sad. Let me give you the link. All right, link. Send a message. All right, let's go. Where's the audio? Let me check the audio. I'm not hearing anything. All right, let's go. Oh, it's not live. Yes, it is. Okay. It's fine. It's fine. Okay, so we're going through this example.
Spinning up on the left, spinning down on the right, and the detector
So this is 3. So I think this is up on the left and down.
simply reveal the underlying quality of the particle that Einstein and his colleagues say is truly the nature of the deep description of reality. Now, so far you say, okay, so John Bell doesn't seem to have done very much. We're just doing the same kind of experiment, but now we just have the choice of picking the axes. But here's the thing. In the three examples that I just gave you, I happened to choose the axes on the left detector and the right detector to be the same. Left was 1, right was 1. Left was 2, right was 2. Left was 3, right was 3. But we don't have to choose. This is the freedom of this new scenario. We don't have to choose the axes to be the same. I could choose different axes for each of the two detectors. Like I could choose on the left, maybe I choose setting number 2. And on the right, I choose 1. Or on the left, I choose 3. Or on the right, I choose 2, and so forth, right? And with this newfound freedom to have different settings on the two detectors, we can now get results quite different from what we've gotten so far. So far, all of our results were this one's up, this one's down, this one's down, this one's up. But now in this case, we can get situations where both are up and both are down. And that's important, as we'll see. So let me take a look at that. So let's do an example.
Okay, so example, left is 3, so it's up. Right is 2, so it's also up. So it's up and up.
Here's a case where you got 3 on the left, 2 on the right in terms of the detector settings. And what's the result going to be? Well, look, the 3 on the left means it's the third arrow, and the triple on the left is pointing up. The 2 on the right means it's the middle arrow for the particle on the right that's also pointing up, and therefore your result will be up and up. A new result, new kind of result we didn't see before. Let me do another example. Let's say I choose my detector settings to be 2.
So left is 2, 2 is down, right is 1, 1 is down. So it's down and down.
On the left and 1 on the right. That means it's the middle arrow on the left that's relevant because it's the second axis. It's the first arrow on the right that's relevant because I chose that.
This guy, regardless of, I don't know if we'll be able to figure this out, but he is one of the, maybe the best explainer, one of the very best explainers. He really brings it down to the lowest level I can imagine. I mean, he's a Columbia University professor, world-renowned, but when he explains, it's like you have to be like, he really dumbs it down to an incredible degree. So really, I appreciate that. Definitely. It doesn't make you feel dumb. He makes you feel smart. So that's very kind of him.
Detector to measure along the first of the 3 possible axes. So that means I'm going to get 2 on the left, which is spinning down, and
okay, 2 on the left is down, 1 on the right is
1
down.
on the right, that's also spinning down. So I should get down, down, and what do we get? Down, down. The detectors work. They do exactly what
The detectors work. Okay.
they are meant to do. And so what this means is if I then run many, many versions of this experiment, particle pair after particle pair going toward the detectors, as they're in flight, say, I have, a team of physicists at the left detector, team of physicists at the right detector, and they're, say, randomly picking the axes. What will happen is we'll get a whole slew.
A whole slew, left, up, right, down.
Of different answers. Sometimes it'll be up and down. Sometimes it'll be down and up. Sometimes it will be up and down. Sometimes they'll both be the same. In that case, it's down, down. So you can then imagine doing this experiment over and over and over again and just collecting a whole lot of data for the outcomes. And here's where Bell's insight comes to the fore. Bell argues, and I'll show you the argument in this case right now. Bell argues that if you do this experiment many, many, many times, randomly choosing the detector settings on each run of the experiment, he argues that the results in which they are anticorrelated up and down, at least 5/9 of the time, the particles have to have that disposition as opposed to this or this. A prediction that emerges from this view of reality, that particles have definite spins along all of these axes that are being measured. Let me show you how the argument goes. It's quite simple. So if you think about it, there are obviously 9 combinations of possible detector settings. 1 on the left, 1 on the right, 1 on the left, 2 on the right, 1 and 3, 2 and 1. You've got 3 possibilities for the left detector, 3 for the right detector, 3 times 3 is 9. So there are 9 possible joint settings of these 2 detectors. And what I want to do, following David Merriman's version.
So there's 9. Right, so it's pairs because there's 2 detectors, so it's pairs. So you could choose left is 1, right is 1, or left is 1, right is 2, left is 1, right is 3, and then the same thing for 2, and then the same thing for 3. So there's 9 ways to run this experiment, okay?
Of John Bell, I want to analyze the results that we will get for one particular value of the spin of the 2 entangled particles. So let's just look at an example of that here. So imagine that my particle is up on the left, down, up, down on the right. Now, I'm just going to go detector setting by detector setting to see what I would get. So if the detector settings are 1 and 1, first axis.
Okay, so they're opposite. They're just opposite, okay. But did he ever explain the rules of this experiment? The results are always opposite? Let's assume that it's always opposite. Okay. So let's go through all combinations.
In both of the detectors.
So 1 and 1, that's up and down.
Because then it's the first arrow in each of the triples that matters, so I get up and down. What if the detector setting
I'm going to assume he's going to do 1, 2. So, well, the first one, it's all ups. And then 2 and 3, it's up and down.
Was, say, 1 on the left and 2 on the right. Then it's the first arrow on the left, and it's the second.
So 2 is up, so it's up and
arrow on
up.
the right, that's an up.
And the third one is going to be up and down.
Up. And now you see I can just continue to fill in the table. I've got the data in front of me. So if it was 2 and 2, it'd be the second arrow, that'd be down and up. 2 and 3, it'd be down and down, because I now have the down arrow from the particle on the right and so forth. All right, so I continue to fill in the table. Now let me look at the number of outcomes in which the spins are opposite to each other. I'm just going to highlight those so we have them up on the screen.
Why do you care about the ones that are opposite? Anyway, but 1, 1, 1, 3, 2, 2, 3, 3, and 3,
and there
1.
You have it. Those are the only ones in which they're opposite. And we got 1, 2, 3, 4, 5. 5 out of 9 of the outcomes have the spins pointing in opposite directions. Okay, that was just one example, though. Let me do another example for you. This was an example where particle on the left was up, down, up, particle on the right, the entangled pair partner was down, up, down. Let's look at another possibility. Let's just, for instance, look at a particle on the left-hand side where it's up, up, down, and therefore down, down, up. Now, as you can see, it's the same basic analysis. It'll just, the results will be shifted around a little bit. So I fill in the table just so you can sort of see it. Again, let me focus on those that have opposite spins, which results have opposite spins. And again, 1, 2, 3, 4, 5 out of the 9 possible outcomes have the spins being opposite. Now, you might say, well, yeah, you're only looking at very special cases. But if you have 2 particles and 3 axes, then at least 2 of the spin directions have got to be the same. There are only 2 possible spins, up or down. You have 3 possible axes. So you can have 2 of them the same at least. The only situation that's fundamentally different from the example that I've been looking at here is a case when all of the spins are the same. So let's look at that case. So imagine on the left particle, you have up, up, up. On the right particle, you've got down, down, down. Now, every outcome along every measurement combination of the axes will give opposite answers. So in this case, you'll have 9 out of 9 giving opposite spin results for these 9 possible measurements. So it's 5 out of 9 when all the spins along all 3 axes are not the same. It's 9 out of 9 when they are the same. Therefore, if you imagine running this experiment over and over and over again, where you're just looking at random entangled particles with random detector settings over a huge number of runs of this experiment, at least
5, could be 6, 7, 8, between 5. It's got to be between 5 and 9.
5/9 of these results will have opposite spins on the left and the right. At least that, because some of them will have it 9/9 of the time. So on average, it's at least 55% of the time you will get opposite spin results. That is a prediction of the Einsteinian view of the world, that particles have definite spins prior to them being measured. And here's the thing. You can now test this result. You can do the experiment. There's nothing really Gedanken-like. These aren't thought experiments. I mean, when Bell first wrote this down, he knew that in principle you could undertake these measurements. They really weren't undertaken fully until the late 70s, early 80s. They've been refined ever since. And here is what happens. When you actually do this experiment, you do not get opposite spins 5/9 of the time. You get opposite spins less than 5/9 of the time. In fact, you get opposite spins 50% of the time, not 55% of the time. And therefore, Einstein's view of the world is in conflict, not with our intuition, not with our desire for how the world should be. It's in conflict with actual experiments that are delineating how the world is.
Okay, this makes no sense. You can't tell me this makes sense. You cannot tell me here are the rules of the game, but the result is a violation of the rules of the game. So either you can't, that has nothing to do with quantum mechanics. This has to do with logic. This is impossible.
And I should point out, the result that you do get from the experiments agrees with the calculation that comes out of standard quantum mechanics. Standard quantum mechanics, without this idea that particles have definite features, that particles truly are in this fuzzy mixture spinning up and spinning down at the same time, it agrees with the experiment, but Einstein, Podolsky, and Rosen's version of reality does not. Now, what are we to make of this? Well, you might immediately conclude that Einstein's view that particles have definite features is what's being ruled out here. And based on how I describe things, I don't blame you for thinking that way. But let me now take you back through the chain of reasoning. Einstein said, the world is not spooky. You don't have an influence here affecting something else over there. And in order to get rid of spooky action, he envisioned that particles had definite features. So the whole point of the Einstein-Podolsky-Rosen view of reality is to get rid of spooky action, to get rid of non-locality by saying that the particles don't have to correlate their behaviors over long distances. They already have definite features and the detectors are simply revealing those features. So Einstein is really assuming that the world is local and that the world has these qualities, hidden variables, it's often called, these hidden qualities, these definite features, even if they may be beyond our ability to know about those definite features until they are measured. So that view of reality is being wiped out by these measurements. And so what we're...
Wait, we have a message on boss. YH, bro, I don't make sense. What is YH? You honestly? Bro, I don't make sense. I don't know. I don't know what you want. What do you want from my life? But a question is, look, you tell me here are the rules of the game. So whatever the rules are, so it's got to be 5/9 of the time we have to have a special, a certain answer. We based on the rules that have been laid, the answer must be 5-9. That's based on the rules. Now you coming in and telling me, well, that's not what we get. All right, then what you told me is wrong. You cannot have it both ways. You cannot have it both ways. You have to make up your mind. It's nothing to do with quantum mechanics. It has to do with the English language. You're telling me, well, it's got to be 5-9. All right, but when we test it, it's not. Well, then it's not 5-9. Well, what do you want from me? You cannot have it both ways. You cannot tell me these are the rules and violate your own rules. You cannot. 1 second. I'm saying this doesn't make sense as the quantum theoretically explains the definitive of this. I don't know what that means. I don't know. I don't know what he said when he said, well, that's what quantum mechanics predicts. What do you mean that's what quantum mechanics predicts? I don't understand. He skipped over a step there. That was skipping over. So I don't know what's going on. It just doesn't make any sense. I'm trying to hear what I misheard. I'm trying to find out what I misheard. I must have misheard something. I must have misunderstood something. This doesn't make any sense. I followed, more or less the mechanics of what the experiment, how it's going to run. You told me, you know what? We can listen to it again. We might. Let me finish, and then we'll try listening again. You have another message. I have a point. Well, yeah. I mean, look. Einstein must be correct. I mean, otherwise, it doesn't make any sense. You can't just come and say nonsense and tell me, yeah, nonsense, yeah, nonsense. I don't know what that means. So either I misunderstood you misunderstood yourself. I mean, I don't know what's going on. This doesn't make any sense. So our job as scientists is to make sense of the world. To come and tell me that the world doesn't make any sense, for that, I have beautiful women telling me that the world doesn't make any sense. And it's my job to make sense of the world for them. So for me to submit to this nonsensical world, I'm not a beautiful girl, so I don't have that luxury. I have a job. I have one job. That's it. Make sense of the world. That's my job. Einstein was correct to a point, however, he can still be disproved. I don't know what it means for Einstein to not be correct. I don't know, because I just don't know how the universe can work. You just told me the rules of the game, and then you told me the results violate the rules of the game. So I don't understand you. Apparently, I did not understand you. So something is wrong with the experiment. Either, look, I cannot trust. Professor Brian Greene telling me, well, they tested and this is what they got. I don't care. I've seen people mess up everything. Every time I trust people, they mess up. Not because they are whatever. That's just nature of reality. Nature of reality is that we all mess everything up, and we all need to be checked and double checked and triple checked and checked and checked and checked and checked and checked. We mess up at every point. As much as can be messed up, we mess up. So to tell me, well, they did this, trust me, bro, they did it, this is what they got. I don't know. I don't know. And even if I would run it, I would have to rerun it and rerun it. I would have to make sure, because this doesn't make any sense. You just told me a bunch of rules, and then you told me these rules are violated. So I don't know. Okay. Let's continue listening to Professor Brian Glean. Professor!
We're really learning is the world cannot be local and have these hidden qualities. Now, it cannot be local.
I wouldn't even say that. I mean, what is the explanation? What do you mean it's 50%? I don't know. I mean, you just showed me it has to be 5/9. It can never be less than 5/9. How could you tell me it's 50%? That doesn't make any sense.
Local and have these hidden qualities. But what that's telling us, therefore, is that in principle it could be non-local and have these hidden qualities. That's not.
What do you mean non-local? I don't even know what that means. I don't know. I mean, explain to me the scenario in which it's as you say. So what are you telling me? You're telling me that there's non-local communication? It's not just communication, there has to be intelligence. If you can have non-locality, then you have non-causality. Then let's travel to yesterday and modify it. So the universe becomes unbalanced. That doesn't make any sense. We cannot have that.
Ruled out, or it can simply be non-local and not have hidden qualities, which is the approach that standard quantum mechanics takes. But the bottom line is, what's really being ruled out by this whole analysis is that the world is local. We're learning that these particles behaving like this and like this are making use of a non-local connection in the manner that standard.
No. How? The universe, we know that the only way the universe makes sense is mechanically. Instantaneous communication is non-mechanical. So that it's a violation of science, which makes it nonsense for me.
Quantum mechanics shows should be there. So that is the import of this whole analysis of Einstein, Podolsky, Rosen, John Bell.
I'll tell you this much. I've never seen anyone explain Bell's theorem so simply. So that's a good job. But let's keep listening. I mean, he is relying on us believing that we believe the experiment.
It's to come to a conclusion that this vision of the world that comes down to us from Isaac Newton, that the world should be local. We learn.
This is not from Isaac Newton. Why are you saying Isaac Newton didn't believe in propagation? In propagation, he didn't have a theory of gravity. He didn't believe in the propagation of information. I don't know why you say it's Newton. Newton did believe in a mechanical universe, yes, but Einstein did too. I think it's the foundation of science. It's the very the definition of science. Wait, let me check a message. Check a message. It's fine.
That picture runs afoul of the quantum mechanical measurements of quantum mechanical systems establish that that picture is ruled out. The world has non-local qualities. Now, I said that with a certain degree of firmness, and now I just want to take a baby step backward, because it's very hard in physics to have fully airtight conclusions, and it's always a matter of.
Exactly. I mean, every experiment we ever conducted is not airtight. Suddenly we have airtight in quantum mechanics. Yeah, that's bizarre. 1 second. Let me check messages. So Aun Boss says Einstein's theory of general relativity, while groundbreaking, is considered incomplete or incorrect in certain contexts because it cannot fully explain quantum phenomena or reconcile with the principle of quantum mechanics, suggesting the need for a more unified theory of physics. Okay, so you must be new. Yeah, I've never seen you here before, but on this channel, we've already resolved special relativity and general relativity with quantum mechanics. That's not the issue. So we've resolved everything thus far. The only problem right now is Bell's theorem. And Bell's theorem, I'm beginning to understand it, so I think I'm going to crack it, I don't know, hopefully soon. All right, let's continue. You're asking good, you have good comments, Aoun boss, very good comments. Thank you for your input.
Of what assumptions you're making, what paradigm within which you're working. And as I've mentioned a few times in these episodes, quantum mechanics, many of us believe, is not yet
Talk.
a subject in which every T has been crossed and every I has been dotted. There is this issue of the quantum measurement problem. And measurement is all part of the story. What's the quantum measurement problem? We don't know how. Even in standard quantum mechanics does not tell us how the world transitions from a fuzzy mixture of up and down or fuzzy mixture of particle being at various potential locations to the single definite reality upon measurement. We don't know how that happens. And without knowing how that happens, there are potential loopholes to any conclusions that we draw. For instance, there is an approach to quantum mechanics called the many worlds interpretation of quantum mechanics. And it highlights, in essence, a third hidden assumption behind everything that we are doing here. Take the Einsteinian view of the world. Einstein is saying the world is local, assumption number one. The world, therefore, has hidden properties in order to explain long-distance correlations. Number three, Einstein is also assuming that when you undertake a measurement, it yields one unique answer. We are assuming that when these particles go to these detectors, the detectors are yielding one answer, up or down. The many worlds approach challenges that. The many worlds approach says, if the particles in this mixture of up and down, then
yeah, many worlds. I cannot accept many worlds. That's nonsensical. I don't know. As Brian Sutter, what's his Sutter? Brian Sutter. What is Dr. Sutter's first name? I don't remember. Josh. So he said. With the many worlds. He said, how does this split occur? What's the mechanics of the splitting? It's ludicrous. It's unacceptable.
when it's measured, you get up in one universe and down in another universe. You get both answers if you look at the totality of this larger reality that encompasses all of the universes. And therefore, that's another way.
So every quantum interaction in the universe causes a split of universes. So you have trillions and trillions and trillions and trillions and I'm gonna say trillions until I'm blue in the face. And that's just to cover one droplet of water. So for the entire universe, we're not even talking about the visible. We're talking about the entire universe. Every microsecond, every nanosecond, you have trillions and trillions and trillions of universes splitting, and each one of those needs to split. So it's ridiculous. It's absolutely ridiculous.
Out from the conclusions of this John Bell theoretical result together with the experimental measurements. You could, in principle, have a universe that's local, doesn't have these definite.
Check messages.
Qualities, these hidden variables, these hidden qualities, and scoots around the incompatibility with the experimental measurements by saying measurements don't have unique outcomes. That is another way to violate the conclusion and in that way be compatible with the experimental observations. Putting that to the side, so that's an interesting possibility. Maybe I'll talk about many worlds in a subsequent discussion.
No, please don't bring up many worlds ever again.
Allow me to put many worlds to the side. I mean, that's so far out in our view of reality that so radically changes our description of the world that I would not consider that in some sense as restoring us to a more familiar view of the world. That's a
Yeah, that is as ludicrous as can be. That's as far away from your job as a scientist.
that's even more extreme, if you will, than the non-locality interpretations. Let me just put that one to the side for a second.
Yeah, non-locality, we can somehow live with it with a non-mechanical universe. You know, you could live with violations of time travel much better than with splitting universes. Impossible, relatively.
But so putting that to the side, we are led to the conclusion that the world is not local, that the world allows these non-local influences. You do something here and it can affect the outcome of a measurement over there. And this is
No. It's not the problem. The problem is that it has to be instantaneous. It has to violate the speed of light, which we've never seen evidence that anything can violate the speed of light. So how does that happen? What's the mechanics by which the speed of light is violated? Why have we never seen this violation happening, except for when we're not looking? That's very similar to how people tell me, I believe in God. Oh, what's your evidence for God? Well, you have to believe him so he will talk to you. All right, I believe him. Why is he not talking to me? No, you have to really well, I'm go ahead. I believe. Well, I don't have a problem believing in God for him to talk to me. I'm completely opening my heart. God, talk to me. No. You're not believing enough. Okay, so I never believe enough, though. So we've never seen the speed of light being violated. There is no violation of the speed of light. We always look and always look and always look, and it's never violated. And it's always constant. I still have to publish the paper. Anyway, wait, is this another comment? I never know if I answered the comment. Oh, wait. So this was your previous comment? Okay, let's see. So the Bell theorem itself isn't considered incorrect. Rather, it demonstrates that certain interpretations of quantum mechanics are incompatible with local realism. But if I'm assuming local realism for reality to be local and real, whatever that means. I mean, local, I understand. I don't know what it means, realism. Whatever. I mean, I'm assuming I'm assuming the known laws of physics. So Bell's theorem disproves the laws of physics. 1 second. Okay. Rather demonstrates that certain. Okay. Further, you say, suggesting that any theory of quantum mechanics must either involve non-locality or abandon the idea that particles have definite properties independent of observation. Okay, I mean, I understand I'm beginning to understand the implications of Bell's theorem, but I have not accepted the results yet. I haven't given up. All right. Let's continue.
This is now coming not from pure theorizing. This is coming from a blending of theoretical insights that start with Einstein, Podolsky, and Rosen. People think that there's no experimental consequence to this view of the world, that it's local and particles have definite qualities. People think that it's metaphysics. John Bell comes along and shows that it's not metaphysics. And others come along, Clausier, Espay, and others, they do these measurements, and they show that Einstein's view of the world is not compatible with the observations. And something's got to give. And at least in the traditional description, putting many worlds to the side, the thing that has to give is that the world is local. All right, that is a stunning conclusion. This has been a longer episode than usual, but I hope.
The thing that has to give is that the world is local, but that's something we cannot give, so I don't care. So we have to assume local, meaning we cannot violate the laws of physics. That's unacceptable. I cannot nilly-willy violate the laws of physics. So the question is, what's left? So we need to understand this experiment.
That you found it worthwhile, because these ideas they're just like spectacular. These are the ideas that make you really sit up and recognize that there's so much more to the world than you think based on everyday observation. What can be more exciting than that? All right, so this Bell result, this Bell theorem is your equation for today. That is your daily equation. I look forward to seeing you at the next episode. Until then, take care.
Well, why is this a theorem? Why is Bell's a theorem or an inequality? I don't understand that. I mean, it's just, what is it? It's a thought experiment. It's a Gedanken. It's an experiment. Okay. What is this? Your daily equation. 8 minus 2 divided by 2 times 3. Okay. Why John Bell deserved a Nobel Prize. Equals mc squared. Is the universe non-local? Is Einstein wrong? Bell's inequality. So what I usually do in these circumstances, I try and listen to short videos with, anyone who suggests a solution, I listen to them. Okay, what is this? The great Bohr-Einstein debate, quantum entanglement, and the great, who is this? Oh, PBS. When was this? Let's go listen to this.
Is there a hidden physical reality that underlies the strange behavior of the quantum world? Or is that reality?
But there's no Bell's theorem. Maybe they'll discuss it.
An illusion in the eye of the observer? The weird phenomenon of quantum entanglement gives us quite startling clues to the answer. Babies may suck at math, but they're actually surprisingly good at quantum mechanics. Well, one fundamental aspect of it anyway. The peekaboo game is thought to be so hilarious to babies because they lack object permanence. Hide your face with your hands and a baby won't automatically assume that you kept existing. Reveal your face again and it's as though you popped into existence from nothing, which is of course a hilarious thing to do. Kids get over this pretty quickly as they learn that things don't magically pop into and out of existence for no reason. By the time they grow up and go to college to study physics, the notion of object permanence is so deeply embedded that we don't even bother teaching it in Physics 101. And yet the idea that the universe keeps existing when we're not looking at it is a pretty fundamental implied assumption behind all of classical physics. Indeed, most of science takes it for granted that the universe is real whether or not we're looking at it. This notion that the universe exists independent of the mind of the observer is called realism in physics. But quantum mechanics is so bizarre that it still has scientists wondering if we need to reject even this basic premise. This was the source of one of the most heated debates at the advent of quantum mechanics. On the one hand, Niels Bohr insisted that it was meaningless to assign reality to the universe in the absence of observation. In the intervals between measurements, quantum systems truly exist as a fuzzy mixture of all possible properties, what we call a superposition of states. In between observations, the wave function describing this superposition.
That doesn't make any sense. It doesn't make any sense. It's a non-mechanical. How does it, what does it mean to be fuzzy? I don't know what it means to be fuzzy. I need a mechanical universe. If you don't offer me a mechanical universe, then I don't know what you're offering.
Is a complete description of reality, and our experience of a well-defined material universe only has meaning at the moment of measurement. This peekaboo.
This doesn't make any sense. Why should the measurement be relevant to anything?
universe is the heart of Bohr's Copenhagen interpretation. On the other hand, Albert Einstein insisted on an objective reality, a reality independent of our observation of it.
I agree with Einstein.
He insisted that the wave function, and by extension quantum mechanics, is incomplete.
The wave function is just looking at the data. It's just the data of what we've observed, and based on that, making a prediction. It's just, we conducted a double slit experiment, we got data. Based on this data, we predict the future. But it's based on data. It just reproduces the data. So that's all that the wave equation is. Not even, I mean, we can ask the wave equation to give us a prediction for a particle to show up with a certain probability at a certain time and space. So, okay.
There must exist what we call hidden variables that reflect a more physical underlying reality. In an effort to demonstrate the silliness of Bohr's idea, Einstein, along with Boris Podolsky and Nathan Rosen, proposed a quantum scenario that showed that in order to abandon the assumption of realism, you also had to abandon a concept almost as sacred: locality. Locality is the idea that each bit of the universe only acts on its immediate surroundings. This is fundamental to Einstein's relativity, which tells us that
basically the laws of physics. It's the laws of physics apply, which goes without saying, but apparently you need to say it in a separate principle.
Chain of cause and effect can't propagate any faster than the speed of light. The Einstein-Podolsky-Rosen or EPR paradox introduces one of the most mysterious ideas in quantum mechanics: quantum entanglement. Here's the idea. Two particles interact briefly, they influence each other so that their properties are somehow connected, and yet we refrain from measuring these properties to preserve quantum uncertainty. Quantum mechanics requires that we describe a particle pair with a single combined wave function that encompasses all possible states of both particles. We call such particles an entangled pair. Now, according to the Copenhagen interpretation, any measurement of one particle automatically collapses the entire entangled wave function and so affects the results of measurements of the other particle. That's an influence that could theoretically be transmitted.
What's an example? Did you write another comment? I don't think so.
Instantly across any distance, and even back in time, violating locality and possibly violating causality. Einstein et al. Thought this was very silly. They thought that every spatial point in the universe must be real and physical and defined by knowable quantities, local hidden variables that could affect each other no faster than the speed of light. The argument between Bohr and Einstein felt a bit philosophical at the time, but in 1964, Irish physicist John Stuart Bell proposed an experiment to resolve the debate. It involves entangled electron and positron pairs. When spontaneously created from a photon, these particles will always be spinning in opposite directions to each other. However, until measured, we can't know which direction either is spinning. We just know that they're opposite each other. Their wave functions are therefore entangled. Measurement of the spin of one of these particles tells us the spin of the other, no matter how large the distance between them. But in quantum mechanics, measurement actually affects the thing you're measuring. In the case of quantum spin, that measurement effect is especially weird. We define spin direction according to the spin axis. That axis can point in any direction. But to measure spin direction, we need to choose an axis.
That's it. You already violated locality. With what you just said, you already violated locality. So that already cannot be. Why do you say that? Then something is wrong already. If you're telling me that it's an entangled pair, which means they can be separated, and then measuring one affect the other, so that now you can conduct the other experiment in the same direction, but there's no way you can know. So how do you know this? There's no way you can know this unless you decided ahead of time to conduct the same experiment. So the first one that conducts the experiment sets the other one to that direction?
To align our measuring device. We always find that the observed quantum spin aligns itself with our chosen measurement axis. If we choose to measure vertically, the spin will turn out to be up or down. If we measure horizontally, it'll be left or right. Measurement forces the alignment of the measured particle. But how does this affect the spin of its entangled partner? The answer would settle the Bohr-Einstein debate. Let me explain. Scenario 1, if Einstein was right. Imagine the response of each particle to all possible spin measurements is encoded in each particle at the moment of their creation, as hidden variables local to each particle. Nothing we do later to one particle will then affect the other. When we later measure the spins of both particles, there will be a correlation in the results because the particles were once connected, but there'll be no correlation due to our choice of measurement axis. Scenario 2, Bohr was right. What if, between creation and measurement, the electron and positron only exist as a wave function of all possible states? In that case, measurement of one particle's spin should
I mean, it's okay for a particle to exist in all possible states because it's a wave and it doesn't really have a spin until you measure it. When you measure it, it collapses and then the spin comes out. But the spin should have been there all along. Just it only really spins. It's like you could say it's like a black hole. It spins really slowly as a star, but then when it collapses, it spins like crazy because it collapses. It's like the collapse of the star. It speeds up incredibly, and then it really. You look at the sun, you can barely tell that it's spinning. How would you even tell that the sun is spinning? You can barely tell. But when it collapses, it starts spinning like crazy. So it could be that the wave is the same. The wave you can barely tell, maybe you cannot tell that the wave is spinning, but when it collapses, because you detect it, then it regained the spin. I would say the spin had to be there all along.
Cause the entire wave function to collapse, to take on defined values. Both particles should then manifest opposite spins along whichever axis we choose for one of the particles. That should lead to a correlation between our choice of measurement axis for the first particle and the spin direction then measured for the second. This is exactly the spooky action at a distance that made Einstein so uncomfortable. So John Stuart Bell figured out a set of observable results.
What do you mean it made Einstein so uncomfortable? So this is already the issue. I mean, you don't need Bell's theorem. This is already the problem. If you're telling me that by observing, by measuring one, you're affecting the other, which could be across the universe. That's already how? You have to explain to me how that happens. If you don't explain to me how that happens, then don't say it. So Einstein said, yeah, it's hidden variables. And everybody said, okay, it's hidden variables. But then came in John Stuart Bell, and he proposed an experiment that shows that that's impossible. There cannot be hidden variables. Einstein said, yeah, hidden variables. There's no spooky action at a distance. John Stuart Bell proposed a proof it cannot be hidden variables. So that's what he's coming to show. He's coming to show that there are no hidden variables. If that's true, then the question goes back to Einstein. Einstein offered an explanation, hidden variables. But now Einstein is going to have to retract hidden variables. So how do you get spooky action at a distance? We don't know. So we have to reject John Stuart Bell. Let's try to reject John Stuart Bell.
Results, the so-called Bell inequalities, that we'd expect to see in the case that Einstein was right and quantum mechanics needs local hidden variables. But if an entanglement experiment violates the Bell inequalities, then local realism is also violated. By the way, Veritasium describes this experiment in much more detail in this video. I recommend you check it out. It's a tricky experiment because entangled quantum states are hard to produce, but even harder to sustain. Any interaction can destroy the entanglement. But in the early 80s, French physicist Alain Aspect succeeded. Instead of looking at the entangled spins of an electron-positron pair, he used photon pairs with entangled polarizations. Polarization is just the alignment of a photon's electric and magnetic fields, but the principle is the same. And Aspect found that there was a correlation between the choice of polarization measurement axis for one photon and the final polarization direction of its entangled partner. The Bell inequalities were violated. The experiment was even set up so that the influence had to travel between the photons at faster than the speed of light. Since then, many experiments have verified this result over larger and larger distances. The instantaneous influence has been observed over many kilometers at this point. The delayed choice quantum eraser, which we already covered, is yet another example of this strange result. It's now been thoroughly confirmed that the Bell inequalities are violated, suggesting that the wave function cannot have local hidden variables. So does this confirm the Copenhagen interpretation and kill both locality and realism? Do we live in a peekaboo universe that vanishes into quantum abstraction when we aren't looking at it? Are babies really better at quantum mechanics than Einstein? Well, not so fast. The results of these entanglement experiments do seem to violate local realism, but that may mean a violation of realism or just of locality. In fact, it was Dr. Bell's opinion that the violation of his inequalities disproved only locality. Realism could be salvaged. Non-locality requires that entangled particles affect each other instantaneously. That sounds blasphemous to anyone who accepts Einstein's theory of relativity. However, non-locality and relativity can actually be perfectly consistent. Relativity requires that causality is preserved, so no faster than light information flow. But none of these entanglement experiments allow any real information to be transmitted between particles. It's only possible to see the influence between the entangled partners after measurements have been made and those measurements are compared. Just as we saw with the delayed choice quantum eraser, the universe seems to conspire to avoid the paradox of information traveling faster than light or backwards in time. The Copenhagen interpretation remains consistent with all quantum observations. Niels Bohr's peekaboo universe may be the universe we live in. However, realist and hidden variable interpretations are also consistent as long as they abandon locality. For example, entangled particles may be dimensionally connected by Einstein-Rosen bridges, wormholes, that allow instantaneous contact even between great spatial separations. Also, the de Broglie-Bohm pilot wave theory works by assuming realism and non-local hidden variables. There's even a way around all of this without sacrificing realism or locality. That's the many worlds interpretation. We'll get back to these in an upcoming episode of Spacetime. Last minute announcements.
Okay, let me see.
Tomorrow night, Thursday the 22nd, is PBS.
Okay, so I don't know.
So forth. But the weirdness, the spookiness is that
So I don't know. Right, so he said, well, it's been confirmed, trust me, bro. Which is what Brian Greene said. I don't like it when they say it's been confirmed, trust me, bro. At least show me. I mean, what's did you verify this? Everyone is wrong about everything. So show me that. Show me. I cannot just trust you, bro. Don't call me bro. Don't call me bro. And I ain't your bro. Proof of Bell's theorem. What do you mean proof?
This video is going to be about the proof of Bell's theorem, but I made another video explaining the significance of Bell's theorem, and
She's so hot. But does she show up?
I think it would be really helpful to watch that first. So if you haven't watched that video, then click this link to be taken to it. So hopefully nobody who hasn't watched the other video is still here. Remember that what we wanted to prove today is Bell's theorem, that entangled particles communicate to each other faster than light. Before I start on the details of the proof though, I'll explain the main idea. Last video, I told you guys about something called spin and some weird experimental facts about it. I won't show you how, but it is possible to explain spin in the framework of quantum mechanics. However, say we didn't believe that anything could go faster than light. Then, because of EPR, quantum mechanics couldn't be true. Therefore, we have to look for an alternative theory where nothing ever acted faster than light. We'll call all theories in this category local theories. What this proof is going to show.
Okay, she said go watch something else first. What should we watch first?
This video is going to be about the proof of Bell's theorem, but I made another video explaining the significance of Bell's theorem, and I think it would be really helpful to watch that first. So if you haven't
Watch this first. There's no link. Things we know about spin.
In this video, we're going to start looking at something called spin. Spin was something that was only discovered when people started experimenting on very small things like electrons. I'm going to tell you about some of the experimental facts that they found. Firstly, what is it? We know that normal objects can have all kinds of measurable properties like position, speed, temperature, etc. Spin is another one of these properties that you can measure of a particle. And in the same way that a particle can have different positions and change its position, the spin of an object can take different values and change over time. But unlike these properties, it's hard to describe what it actually is intuitively. Spin of an object, spin is firstly, what is it? We know that normal objects can have all kinds of measurable properties like position, speed, temperature, etc. Spin is another one of these properties that you can measure of a particle. And in the same way that a particle can have different positions and change its position, the spin of an object can take different values and change over time. But unlike these properties, it's hard to describe what it actually is intuitively. The best I can do is say that the spin of a particle measures how magnetic it is and decides which direction the magnetic field is pointing. The problem with this statement is that it makes particles seem like they act like tiny little bar magnets. Actually, they don't, because as we'll see, spin is a very strange thing. Let's just get to those experimental facts and we will return to this point later. From here on in, we're going to be looking at the spin of electrons. Whenever we measure spin, we have to pick a direction. In other words,
Let me go get some gum and a carrot, maybe. I'll eat a carrot. I'm here to chew bubble gum and kick some tushy, and I'm all out of bubble gum. Give me a minute. Mm-hmm. Mm-hmm.
An axis to measure it in. Let's call the direction pointing east the x-axis and the direction pointing north the y-axis. Then say I happen to know that an electron has spin of some strength that I'll call s in the x direction. It's tempting to say that the electron is like a bar magnet pointing in the x direction. But if that was the case, then how much spin would you expect the electron to have in the y direction? Well, the y direction is perpendicular to x, so normally we wouldn't expect there to be any magnetic field that way at all. However, if you measure the spin in the y direction, you will get a very weird result. Say we do this experiment and record the results, then do it again using a new electron and keep repeating. Half the time, you'll find that the particle not only does have spin in that direction, its strength is still s. The other half of the time, it will still have strength s, but this time in the negative direction of y. This is completely unexpected. But notice something. If we take the average of the results, we get 0, which was the result we thought we'd get. Let's try another example. Let's start with the particle with spin s in the x direction again. We'll pick the 45-degree axis to measure the spin in. What would we normally expect? Well, the 45-degree angle axis is still somewhat pointing in the x direction, so we expect that there is some spin in that direction, but a smaller amount than s. We can calculate how strong we think it should be using vectors and get that the new spin should be s on root 2. But what happens when we measure it? Again, every single time we repeat this experiment, the electron will have spin of strength s, but this time it will be slightly more likely to have it in the positive direction than the negative, so that when we take the average of all the results, we get s on root 2. Again, though each individual trial was unexpected, the average result is what we thought we'd get. Let me summarize the two things we can learn about the spin of an electron from these kind of experiments. Firstly, no matter what direction we pick to measure the spin in, its value will always be positive s or negative s, where s is equal to this small number. We'll give these two possibilities some convenient names, up and down. So you can, for example, say that an electron is spin down in the y direction. The second weird thing is that wherever you'd normally expect an electron to have a certain spin in a direction.
No, it's not a weird thing. This is necessarily true because you're measuring an electron. You're not measuring a classical object that can have half of a property. A quantum object, it's all or nothing. You don't have half an electron. Like a bicycle, you can cut in two. A bottle, a glass of water, everything in the macro world you can cut in two. But in the quantum world, that's it. There is no half electron. So it makes sense that you're getting up or down, nothing else. Because when you're interacting with it, you're interacting with it completely, with its entirety. Well, the question is, what is spin? Usually when I ask, they say, no, it doesn't spin. Okay. Well, if it's not spinning, then stop calling it spin. Like, you're telling me, yeah, it's not spinning. Why do you call it spin? Well, it behaves like spin. Okay. But it's not spin. No, it's not spin. Okay. As long as we don't know what it is, right, you're confusing everyone by calling it something that you admit it's not. It's not spinning. Okay. Don't call it spin. Call it weird something. I don't know. You're confusing everyone by calling it spin. You call it spin. You say it's not spin. And then you say it's weird. No, it's not weird because it's not spin. It's not weird because it's all or nothing. That's the quantum world. There's no half electron. Any interaction with an electron is with a complete electron. And I don't know, I certainly don't know what spin is, I've never interacted with an electron. I mean, except for in the winter, you keep getting shocked every time you touch a doorknob. But I've never noticed spin. I'm seeing lightning. I don't see spin with lightning. All right.
Let's say spin equal to k, you will instead find that each time you measure, you will only get spin up or spin down. But when you average the spin of each trial, you get the right result, i.e. averaging your data will give you k. So you see, it's possible to say which direction an electron spin is in and its strength, but it's not really like the classical situation with a bar magnet. With a bar magnet, knowing how strong the magnet is and in what direction allows you to find its strength in all other directions. That's not the case with spin. When there's lots of particles with spin, on average they act just like bar magnets. In fact, that's what a bar magnet is. It's heaps of particles with spin stuck together. But individually, these particles act like they're equally strong in all directions that they're measured in and act randomly. We still don't know if this randomness is true randomness though, and we still don't know what spin really is.
Okay.
This video is going to be about the proof of Bell's theorem, but I made another video explaining the significance of Bell's theorem, and I think it would be really helpful to watch that first. So if you haven't watched that video, then click this link to be taken to it. So hopefully nobody who hasn't watched the other video is still here. Remember that what we wanted to prove today is Bell's theorem, that entangled particles communicate to each other faster than light. Before I start on the details of the proof though, I'll explain the main idea. Last video, I told you guys about something called spin, and some weird experimental facts about it. I won't show you how, but it is possible to explain spin in the framework of quantum mechanics. However, say we didn't believe that anything could go faster than light. Then, because of EPR, quantum mechanics couldn't be true. Therefore, we'd have to look for an alternative theory where nothing ever acted faster than light. We'll call all theories in this category local theories. What this proof is going to show is that, no matter how cleverly we try, we could never come up with a local theory that could explain spin. We'll do that by a proof by contradiction. In other words, we'll start by believing that it is possible and see what happens. There's one particular experiment with spin we'll try and explain. Let's say I have a source of electrons with entangled spins. This means that if A and B are a pair, if I choose to measure them both in the same axis, one will be up and the other down. Now A and B are sent off to two machines very far away from each other, which we'll call L. Now A and B
They've been
measure the
entangled?
entangled spin we'll try and explain. Let's say I have a source of electrons with entangled spins. This means that if A and B are a pair, if I choose to measure them both in the same axis, one will be up and the other down. Now A and B are sent off to two machines very far away from each other, which we'll call Alice and Bob. Alice and Bob can each measure the spin of their electron in three different axes. These are the three axes, and we choose them so that they are 120 degrees apart from each other. When A arrives at Alice, Alice randomly chooses an axis to measure A's spin in, and Bob does the same thing with B. But they do it independently from each other, so Alice could measure the spin around 2, and Bob around 3, for example. If the machines measure their electron to be spin up, then they flash red, or if it's spin down, they flash white. Someone notes if the two machines have the same color or not. This experiment is repeated many times. The question is, what fraction of the time will the colors be different? The answer is actually a half, and if you're willing to take my word for it, then you can skip this next part and move on to the most interesting part of the proof. If not, stick around and we'll figure out why that's the case, using the rules of spin from last time. Let's say Alice measured around axis 1 and happened to get spin down. Let's see how likely Bob is to measure spin down as well. The reason I can just pick a particular case like this is because all the other cases will work out in the same way to the same result. 1/3 of the time, Bob will choose axis 1 as well. So since A and B are entangled, Bob's particle will definitely have spin up in that direction, so the colors don't match. What about if Bob measured around axis 2? Because A is down in the first axis, B must be up in the first axis, so we just have to figure out how much of the spin is pointing in the second direction. Actually, as you can see, this vector is partially pointing in the negative direction of axis 2. What does this mean? It means that if you measure the spin in axis 2, it's either going to be up or down, but more likely to be down. So in this case, A and B are more likely than not going to have the same spin, and therefore the colors are likely to be the same. What about axis 3? This is a really similar story to axis 2. As you can see, this vector is pointing in the negative direction of axis 3. So most of the time, B will be down if it's measured in axis 3. So again, Alice and Bob will most likely have the same color. Let's review those three cases again. If Bob is on axis 1, Alice and Bob definitely won't have the same color. If Bob is on axis 2 or 3 though, more often than not, Alice and Bob will have the same color. It works out so that overall there is an exactly 50% chance that Alice and Bob will have the same color.
It's a really good explanation and a really good experiment. Yeah, it's got to be 50%.
And 50% chance that they won't. Okay, so now we're going to see if a local theory could
Wait, so if they're both 1, it's going to be 0. Wait, why is it 50%? Oh. Okay, why is it 50%? So, well, hear her explanation from the beginning. I missed the beginning. 1 and 1. A third of the time, it's not going to match if it's 1 and 1.
work out in the same way to the same result. In particular case, likely Bob is measured around axis 1 and happened to get spin down. Let's see how likely Bob is to measure spin down as well. The reason and why, the answer is actually a half. And if you're willing to take my word for it, then you can skip this next part and move on to the most interesting part of the proof. If not, stick around and we'll figure out why that's the case, using the rules of spin from last time. Let's say Alice measured around axis 1 and happened to get spin down. Let's see how likely Bob is to measure spin down as well. The reason I can just pick a particular case like this is because all the other cases will work out in the same way to the same result. 1/3 of the time, Bob will choose axis 1 as well. So since A and B are entangled, Bob's particle will definitely have spin up in that direction, so the colors don't match. What about if Bob measured around axis 2? Because A is down in the first axis, B must be up in the first axis, so we just have to figure out how much of the spin is pointing in the second direction. Actually, as you can see, this vector is partially pointing in the negative direction of axis 2. What does this mean? It means that if you measure the spin in axis 2, it's either going to be up or this
So,
to this first axis. Bob's particle.
so Alice picked 1. She got down. Bob, let's say, picked 1. It's up. The question is, what was the question?
Alice randomly chooses an axis to measure A's spin in, and Bob does the same thing with B. But they do it independently from each other, so Alice could measure the spin around 2, and Bob around 3, for example. If the machines measure their electron to be spin up, then they flash red, or if it's spin down, they flash white. Someone notes if the two machines have the same color or not. This experiment is repeated many times. The question is, what fraction of the time will the colors be different? The answer.
That's the question. What fraction of the time will the colors be different? And what fraction will be the same? So she says the answer is 50%. So we each randomly choose a direction. Okay.
The answer is actually a half, and if you're willing, if not, stick around and we'll figure out why that's the case, using the rules of spin from last time. Let's say Alice measured around axis 1 and happened to get spin down.
Well, she measured 1. Let's say she got spin down.
Let's see how likely Bob is to measure spin down as well. The reason I can just pick a particular case like this is because
So if Bob picks 1, he has to get the opposite result. Why? Why do you say that?
all the other cases will work out in the same way to the same result. 1/3 of the time, Bob will choose axis 1 as well. So since A and B are entangled, Bob's particle will definitely have spin up in that direction.
Why? How's that possible? That's already a violation of locality. So I don't know what's going already now. Of course, from here on, if I submit to this point, of course she's going. From here, it's a slippery slope. So we need to go back to the original video. So hold on. Let's go watch the previous video again.
In this video, we're going to start looking at something called spin. Spin was something that was only discovered when people started experimenting on very small things like electrons. I'm going to tell you about some of the experimental facts that they found. Firstly, what is it? We know that normal objects can have all kinds of measurable properties like position, speed, temperature, etc. Spin is another one of these properties that you can measure of a particle. And in the same way that a particle can have different positions and change its position, the spin of an object can take different values and change over time. But unlike these properties, it's hard to describe what it actually is intuitively. The best I can do is say that the spin of a particle measures how magnetic it is and decides which direction the magnetic field is pointing.
Well, this is already the beginning of the end. You cannot tell me there's this thing, I really don't know what it is. But let me build a completely revolutionary way to view the universe based on this thing that I cannot really describe. Okay? That's your answer. So you don't know what spin is. You've never made mechanical sense out of spin. So there's no point. So anything that comes out of this discussion that makes no sense, well, then you can roll back the tape and say, well, that is not spin. If this is the result, right? If spin is X, and because I assume spin is X, the universe makes no sense, well, now you know spin is definitely not X. Or something to that effect. You cannot come and tell me this thing makes no sense, but I'm going to revolutionize the very view of reality based on this thing that I really cannot make sense out of its definition. Yeah, I'm sorry. You're gonna have to excuse me when I tell you that I'm not gonna follow you down that rabbit hole. It's okay to have a rabbit hole if the rabbit hole, you need a rabbit, you need a hole, then it's a rabbit hole. We can go down a rabbit hole, If you're telling me spin is about how magnetic something is and in what direction. What it is. Spin is a property you can measure, can take different values, change over time. That's useless. You need to explain to me mechanically what spin is. I'm tired of people telling me spin is something like this, but really it cannot be this. It's like that, but it cannot be that. But trust me, bro, if we assume spin is spin, which is not, then our view of reality is shattered. Well, in that case, we know spin is not that. So I kept asking you, what is spin? You kept telling me, we don't know. But let me tell you, even though we don't know, we're going to base our understanding of reality itself on the definition of spin. I'm not asking for much. I'm asking for a mechanical explanation of spin. If you're not going to give me a mechanical explanation of spin, then you're going to have to excuse me when I tell you any conclusion you draw from a non-mechanical definition of spin. No, I'm going to tell you that's not to rely on that. That's unreliable. Okay. So they're not basing spin is so confusing. They don't have a mechanical explanation of spin, but then they become so confused when they conduct experiments and they get confusing results. Well, you don't have a mechanical explanation of spin. So any conclusion you have, all it says that, well, that's not spin. Whatever spin is, whatever you assume it is, it's not, if you're getting results that conflict with reality. Because we assumed reality, right? When we start the day, we assume reality. Based on reality, we run an experiment. If the experiment ends up telling us, well, that's not reality, well, then the experiment was bad. The experiment cannot conclude that our reality is not reality, because I might as well assume I didn't wake up this morning, I'm still dreaming, I'm still in my dream from last night. So you cannot tell me, listen, bro, we have this thing that we call spin, but really it's not spin. Okay, then why are you calling it something that really it's not? Why are you doing that? Okay, so why don't we restart this discussion? This time, don't call it something that you know it's not. Call it something that you know it is. Or I don't know, let's not discuss it. I mean, if you're not sure what it is, you don't have a mechanical understanding of what this thing is. So what's the point? Let me check out a message. Yeah, she's hot. Wait. She looks good. Welly, welly, welly. Welly, 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 welly. Welly, 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 welly. Welly, 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 welly. Whoa. Whoa. Very, very deluxe. Very deluxe. Very deluxe. Definitely. Definitely. So we're pretty close to resolving this nonsense. Wow. Wow. Oh my God. Oh my God. Oh my God. Psst. Definitely. Definitely. Oh my God. Oh my God. Definitely. Definitely. Definitely not. Definitely not. Not. Wow. Wow. Very nice. Very nice. Very nice. Very nice. Trust me on the sunscreen. Okay, where's the message? She was about to send a message. Where's the message? Mhm. And okay, okay. Okay, how is the market? We're up 1%. We're up 1%. Let's look at the markets a little bit. A little bit of the market. What's going on with the market? Anyway, but this seems to be the crux. This seems to be the crux. If we're not sure, we're not sure what spin is, but we're assuming something that we know it's not. Because of that, we end up contradicting reality. Then that's it. Then you know that's not spin. You said it's not spin, and now you got a contradiction with reality, therefore it's not spin. Okay. Let me write a message. Let me explain this to Sinus. Okay. I made a significant leap forward. with respect to Bell's theorem. So, is he sleeping? I don't. All right. So, what's the answer? At least when they talk about spin, we don't know what spin is. At least we don't have a mechanical explanation of spin. So we don't know what spin is. Based on an amorphous definition of spin, we end up concluding that reality is not real. That makes no sense. All that we may conclude is that we misunderstand spin. But then I repeat myself. That's it. I mean, there's nothing more to say about this. This thing. Let me check messages. Archive. What is archive? Why is this archive? That's weird. Okay, let me okay. That's the direction of my investigation. That's currently my direction of my investigation. What it is wherein I pretend to have a clue. So this is the foundation of something that violates our notion of reality, where she pretends to have a clue. So the conclusion should be, well, as you said, you pretend to have a clue, you have no clue. I'm not even going to say you have no clue. You say you have no clue. I'm not saying this as a pejorative. I'm just saying it as a technical analysis. If you assume something, right? You pretend to have a clue. Okay, whatever. Let's formulate it as you are assuming. Let's assume it's X. All right. Based on our assumption that spin is X, we get a violation of reality. Oh, good. Now you know it's not X. Done. Very simple. If you assume something, and because of this assumption, you contradict the assumption, done. Right? Part of the assumption is reality is real. laws of physics are real. I mean, we're assuming the known laws of physics. If you end up contradicting the known laws of physics, that's reality. What is reality if not the known laws of physics? We didn't waste 4 billion years to nilly-willy say, well, yeah, so the laws of it, so, I was sitting at home eating pizza and drinking beer and violated the laws of physics. No, that's not acceptable. In order to claim that you violated the laws of physics, we're going to have to be a little bit more careful than just nilly-willy accepting your claim. So you agree that everything that this violation of reality is based on, well, we don't know what it's based on. Yeah, exactly. So it's not based. So you can say goodbye to whatever it is. You need a mechanical explanation. So let's start with a mechanical explanation of spin. We cannot cross this impasse. We have reached an impasse, as they say in South Park. That's it. We cannot continue down this path. This is unacceptable. This is unacceptable behavior. There's a limit to what we can entertain. Right? If we're being scientific, right, you have this very, very scientific, very rigorous, very analytical video. We considered everything. Yeah, but it's all based on pretending to have a clue. Well, then, all right. Then, yeah. Then the pretending didn't, then we need to take that back. And I like Looking Glass Universe. She's hot and smart. No, I don't have an issue with her. This could be the resolution to Bell's theorem. That, if your claim that Einstein was wrong is based on spin that we don't understand, then that's useless. Maybe.
That normal objects can have all kinds of measurable properties like position, speed, temperature, etc.
Temperature. You mean macro objects?
Electrons. I'm going to tell you about some of the experimental facts that they found. In this video, we're going to start looking at something called spin. Spin was something that was only discovered when people started experimenting on very small things like electrons. I'm going to tell you about some of the experimental facts that they found. Firstly, what is it? We know that normal objects can have all kinds of measurable properties.
So if your assumptions end up matching empirical, if you're able to explain with assumptions the empirical results, then okay, it's one step forward. But if you end up contradicting, then it's a bad theory. You cannot contradict the empirical results, right? I mean, what is science? In science, we predict empirical results. One second. The water image. It explains spin in a wave. Okay, when we hear back from him, we'll continue listening. All right, there it is. Let's see. Transverse waves polarized in the same direction, going in different directions, have opposite spins always. If so, I don't know what. No, it's nothing to do with me. I mean, oh, stop. Stop. That has nothing to do with it. We don't understand spin. No. Oh, well. Join me so we can talk. No, I'm not. No. Oh, okay. But think about it. No, I have a direction that is literally opposite. Join me when you can. All right. All right. Okay, so she says,
like position, speed, temperature on very small things like electrons. I'm going to tell you about some of the experimental facts that they found. Firstly, what is it? We know that normal objects can have all kinds of measurable properties.
Okay, normal object.
Like position, speed, temperature, etc. Spin is another one of these properties that you can measure of a particle.
Of a particle.
And in the same way that a particle can have different positions and change its position, the spin of an object can take different values and change over time. But
okay,
unlike these properties, it's hard to describe what it actually is
okay. No, you have to describe what it actually is.
intuitively. The best I can do is say its values and change over time. But unlike these properties, it's hard to describe what it actually is intuitively. The best I can do is say that the spin of a particle measures how magnetic it is and decides which direction the magnetic field is pointing. The problem with this statement is that it makes particles seem like they act like tiny little bar magnets. Actually, they don't, because as we'll see, spin is a very strange thing. Let's just get to the.
So you cannot base the complete upheaval of what we define as real on something that you cannot, that you claim you don't really understand. Whatever this reality is, we understand it. Every little thing about it, we understand. If your definition, if you come to the conclusion that we misunderstood reality all along, that's fine. But if that's your conclusion is based on something you're not sure of, then you're not sure of the conclusion that we misunderstood reality. So you're not saying anything. All you're saying is that probably you're misunderstanding that thing that you're talking about. Fundamentally. You have a fundamental misunderstanding about spin. If you're using spin to distrust our very notion of reality, then your notion of the definition or your notion of spin, well, obviously, I'm not saying obviously pejoratively, obviously as meaning by the very definition of the word obviously, then by definition, you got spin wrong. If spin leads you to conclude that reality is not real, then your definition of spin, your understanding of spin is wrong. That's it.
those experimental facts, and we will return to this point later. From here on in, we're going to be looking at the spin of electrons. Whenever we measure spin, we have to pick a direction, in other words, an axis, to measure it in. Let's call the direction pointing east the x-axis, and the direction pointing north the y-axis. Then say I happen to know that an electron has spin of some strength that I'll call S.
Which you don't understand what it is. You don't have a mechanical explanation of spin. Notice that we have good mechanical explanations of what a particle is. It's a wave. It's waving. It's a Fourier overload, whatever, superposition of multiple waves, so that it has a certain location and velocity and momentum and energy. All these things, we're kind of comfortable with all these things. With spin, I honestly have never heard of an explanation of what spin is. Where is it coming from? What is the mechanical explanation of spin? How is a wave emanating a spin? Where would a wave hold its spin? When a particle wave becomes a particle and it gives off the magnetic field, where was the magnetic field all along when it was just a wave? So we need a mechanical explanation, and until then, we're wasting our time. Certainly, we cannot redefine reality or tear down reality based on something we clearly claim we don't understand.
In the x direction. It's tempting.
I thought it would be so difficult to destroy Bell's theorem, but I see that it's becoming very straightforward. It's rather straightforward.
Tempting to say that the electron is like a bar magnet pointing in the x direction. But if then say I happen to know that an electron has spin of some strength that I'll call S in the x direction. It's tempting to say that the electron is like a bar magnet pointing in the x direction. But if that was the case, then how much spin would you expect the electron to have in the y direction? Well, the y direction is perpendicular to x, so normally we wouldn't expect there to be any magnetic field that way at all.
So we don't know what spin is. We don't know what we mean when we say that it has spin in the direction S, which is in the direction X. We don't know what we mean. We don't know. And then we measure it in the Y, and we sometimes get a measurement. We don't know why.
However, if you measure the spin in the y direction, you will get a very weird result.
If you're getting a weird result, that means you don't have a good understanding. You're saying it's weird. I'm not saying it's weird. You're saying it's weird. If you say it's weird, you cannot build your tearing down of our perception of reality on it. At best, you can tear down your perception of that weird thing because it contradicts our definition of reality. It wouldn't make sense to take something that you consider weird, you admit it's weird, meaning it conflicts with our very notion of reality, assume it's correct, and now that we assume it's correct and it's weird, so tear down our very notion of reality. Of course, that's what's going to happen. 1 second, let me. All right, very nice. Belly nights. We belly good the nights people. Belly nights people. Belly nights. Anyway, so I think we've made very good progress. Oh my god. Very nice, very nice. So that's beginning to look like the direction of the answer. So you assume, right? This is basically proof by contradiction. You assume a definition, the definition leads to a contradiction, or you assume something, it leads to a contradiction. Well, now you know the assumption was wrong. That's proof. That's literally proof by contradiction. So you assumed something, it leads to a contradiction with reality, with the laws of physics. It doesn't matter. Then you can go back and say, oh, then we know it's wrong. Right? What is science? Science is we come up with a theory to explain reality. And if it doesn't explain reality, oh, then we know it's wrong. So go back and try and explain it again. That is the definition of science. So if your theory contradicts reality, oh, then we know your theory is wrong. Keep searching. It's very simple. It's really very simple. You cannot conclude, oh, I discovered today a contradiction to reality. No, you did not. You discovered that your theory is wrong by definition. Because the definition of being correct is agreeing with reality. The definition of being wrong is disagreeing with reality. You cannot tell me, today I realized wrong. No, you did not. You did not. You did not do such a thing by definition of science. As long as you define yourself to be a scientist, it's just the definition of science. It's really that simple. It's really just the definition of science. If your science leads you to conclude that reality is wrong, oh, very good. Then you learn today that your science is wrong, that your theory is wrong by definition. So it's a good day. It's a good day in which you learn that your scientific theory is wrong. It's a good day. I'm going to save you time. Your theory is wrong. Go back to the drawing board. That's it. That's Bell's theorem. That's Bell's theorem. That's all it is. That's all it is. That's all it says. And when Einstein said, whatever you say and it contradicts reality, our perception of reality, well, you have to go back to the drawing board. That's all he said. That's all he said. Just go back to the drawing board. And Bohr said, oh, no need. It's okay to contradict reality. Okay? It's not a disagreement about reality. It's a disagreement about the definition of science. So Einstein understood science. Einstein was already an old man. He understood science. And the rest, they didn't understand the definition of science, including Feynman, including the rest of them, including this video. So whatever the definition of spin is, if it leads you to a contradiction to reality, oh, great. Now you know that's not a definition of spin. It's a good day. It was a good day. It was worth it to wake up that morning and get out of bed. I was thinking about, the other option was to stay in bed the whole day, not face reality. But then I said, you know what? Let me go get some coffee, then we'll rethink our plan for the day. Oh, and then we discovered our definition of spin contradicts our definition of reality. Oh, fantastic. Fantastic. So it was worth it to get out of bed that morning. After all, it was worth it. It was worth it. I was contemplating, get out of bed, not get out of bed. What's the point of getting out of bed? What's the point? It's pointless. Well, you never know. On that day, you might just discover that your definition of spin, your theory, your scientific of spin, you might discover on that day that you thought to stay in bed. You might discover on that day that your definition, your theory of spin, contradicts your perception of reality. Oh, fantastic! Now you know it was worth it to get out of bed that day after all. Fantastic! Fantastic! That's a good day. That in itself is a good day. But Bohr says, no, it was another pointless day. Life is pointless. Einstein says, no, we have a perception of reality. We have a perception, we have a definition of science. If a scientific theory contradicts our perception of reality, it's a wrong scientific theory. You have to go back to the drawing board. Very simple. And Bell comes and he says, no, that's not true. Our definition of science may contradict our perception of reality. Okay? So it's a disagreement about the very definition of science. Einstein says science is mechanical. If it's not mechanical, we don't care. It's got to be mechanical. It's got to be local. It's got to be real. And Bohr says, no, it doesn't need to be local. So this is not about quantum physics. This is about the definition of science. That's it. It's really very simple. So we don't understand spin. Okay, then don't use spin. When you don't understand something and you have a theory what it is, and that ends up contradicting your perception of reality, fantastic. Now you know that's not, your theory is incorrect. Fantastic. Go back to the drawing board, rethink it. Rethink until your scientific theory stops contradicting your perception of reality. That is called science. Yeah, that's that thing. That thing that we call science? Yeah, that's the thing we call science. Science is the collection of theories that do not contradict our perception of reality. Do not contradict the laws of science. If your theory contradicts the laws of science, well, then it's not scientific. The laws of physics. Every law of physics, the foundation, cause and effect, causality. You want to contradict causality? You want a non-mechanical universe? All right. Then me and you, there's no point in having any further communication. And that's it. I don't have anything else to say. So that's it. I mean, I thought I would have something deeper to say. There's nothing deeper to say except for that thing you call quantum mechanics. Okay, you claim you don't understand it. Okay, keep working at it. Keep working at it. You can't say, well, that's our best theory. It's not a theory. If it contradicts your perception of reality, if it violates the laws of physics, then send it back to the drawing board. It's useless. But it's very useful. It's very this. It's very that. Okay, fantastic. Yeah, whatever you want to use it at your own peril. I don't want to use it. Yeah, but we build this, we build that. That's fantastic. Enjoy. I'm staying out of I'm staying out of that. That sounds dangerous to me. I don't know what else to say. That's it. So these people, they want to live in a contradiction. And, all I can say is enjoy. We don't have anything further to talk to each other about. I have nothing to contribute to a discussion with a person that is willing to live with a contradiction. Okay, enjoy your contradictions. I was wondering. She's like, there's this, there's that, but it leads to a complete contradiction with reality. Okay, let's check our assumptions. I was like, let's go listen to the previous video. Maybe, maybe over there we'll find something. Oh, so your theory of nonsense is nonsensical. Your theory of of spin is nonsense, and that's what you're basing everything on. Yeah. Okay. Enjoy.
Say we do this experiment and record
She said do.
the results, then do it again using a new electron and keep repeating. Half the time, you'll find that the particle not only does have spin in that direction, its strength is still S. The other half of the time, it will still have strength S, but this time in the negative direction of Y. This is completely unexpected.
Okay. So if something is completely unexpected, look, you're saying it's unexpected. I'm not judging you. You're judging you. So you cannot come to me and now tell me, well, this is a scientific theory. No, that's not a science. If it's weird, then it's not a scientific theory. It's got a scientific theory needs to be mechanical. So come up with a mechanical theory. Once you do that, then you can implement it and see if that contradicts intuition. Then it's wrong. Back to the drawing board. But you never even got that far. You're saying it's weird. Okay, if it's weird, then it's not a scientific theory. A scientific theory cannot be weird. You could have a temporary, filler scientific theory that it's better than yesterday. That's fine. But if it contradicts reality or perception of reality, then it's wrong. You could say it's wrong, but it's better than yesterday. That's fine, but it's wrong. And all that Einstein is saying is it's wrong. It's better than yesterday. That's fine. It gives you good predictions. That's fine. You can create technology based on that. That's fine. You can make money from that. That's fine. Everything is fine, but it's incomplete. That's all I'm saying. It's incomplete. It's not proper science. That's all. That's the EPR paper. So no, let's not misunderstand EPR. EPR is about the definition of science. That's all. Okay, I think, well, as far as I'm concerned, that is the resolution. Resolved. So I resolved, let's just rename it to I resolved research. No, I resolved Bell's Bell's inequality theorem, whatever. Bell's theorem. Bell's inequality? I don't know. I don't even know what theorem, what inequality. He has proof. So I resolved it. And it was very simple. It is actually very simple. Yet deep. It's as deep, it's as deep as you can imagine. It goes to the heart of the definition of science. It goes to the heart of the EPR paper. So no one talks about the EPR paper. Okay, so let's go to, maybe we should read the EPR paper. But anyway, I'm done. I'm done with this nonsense. So I was very excited to try and figure out Bell's inequality. I was really excited. There's nothing to it. There's literally nothing to it. It's just a misunderstanding of the EPR paper. It's maybe Einstein didn't express himself. It's a conflict of definition of science. It's about the definition of science. It's not about physics. It's not about quantum mechanics. It's just the definition of science. That's all. And that's it. I don't know what else to say. I mean, we can go back to the EPR and read it, but I read the EPR paper a little bit, just a very little bit of it. And all it says is quantum mechanics is incomplete. That's all. So to come and tell me, well, quantum mechanics is complete and it contradicts reality, well, all that Einstein said is if it contradicts reality and realism and locality, yeah, it's incomplete. To come and tell me, no, it's complete. No, that's the definition of incomplete. Let me be clearer, Mr. Bell. So Bell completely misunderstood everything, and everyone misunderstands science because the definition of science has become so corrupted. Science is allowed to contradict reality and locality and a mechanical universe. So at this point, science has become a religion, a backwater or a backwards religion, an ancient religion from the ancient times, from the pre-scientific revolution. So science today has reverted into the pre-scientific, the pre-enlightened age. So science today is no longer, it went back to pre-enlightenment. So the whole notion of enlightenment is we can figure out this world. And that's it. We lost. The scientific revolution, we can declare the scientific revolution to be over. If people say that the Bell's paper is worth the ink, it's not worth the ink. He misunderstood the EPR paper. He misunderstood what Einstein, Rosen, Einstein, Podolsky, and Rosen had to say. And there, I think Einstein should have just involved a philosopher of science. A philosopher of science would have explained it maybe better. I don't know, with the way science, the shape of science today, I don't know. But that's the problem. So instead of sitting down and figuring out, all right, so what is this spin? What is going on? Because that's, for me, like I'm still wondering, what the heck is spin? What is it? I'm not willing to just say, well, it's not this, it's not that, we don't know. But, But it's very weird. Yeah, but let's assume whatever it is, it contradicts our notion of reality. Oh, we disproved reality based on spin. What is spin? Oh, we don't know. We don't know. Oh, so you don't know what reality is? No, we don't know. We don't know. But reality is not real. Oh, that's good to know. Always good to know. Anyway, it's a complete waste of time. The last thing I expected to conclude is that Bell's theorem is a complete nonsense waste of time. Botch it up, and how could everyone take it seriously? That's the question. How does that happen? Right? She says, where is it? Where is it?
Then say I happen to know that an electron has spin of some strength that I'll call S in the x direction. It's tempting to say that the electron is like a bar magnet pointing in the x direction.
What do you mean it's tempting?
But if that was the case, then how much spin would you expect the electron to have in the y direction? Well, the y direction is perpendicular to x, so normally we wouldn't expect there to be any magnetic field that way at all. However, if you measure the spin in the y direction, you will get a very weird result.
Right? She says weird. You can't say that. That's not science.
Say we do this experiment and record the results, then do it again using a new electron and keep repeating. Half the time, you'll find that the particle not only does have spin in that direction, its strength is still S. The other half of the time, it will still have strength S, but this time in the negative direction of y. This is completely unexpected.
Unexpected. That's not science.
But notice something. If we take the average of the results, we get 0, which was the result we thought we'd get. Let's try another example.
Suspicious. The result we thought we'd get. Something suspicious is happening. You cannot base a proof that reality is not real on this. I'm sorry. So you have to figure this out. And this is not a mechanical explanation. So not only is it not mechanical, it's suspicious, it's weird, it's unexpected. That's you saying these things. So you cannot, and it's not mechanical, so you cannot come to me after billions of years and tell me all the science goes to the garbage because this suspicious, unexpected, weird, non-mechanical, non-explanation I have of a phenomenon contradicts reality. I'm sorry. Go back to the drawing board, rethink your definition of spin.
Let's start with the particle with spin S in the x direction again. We'll pick the 45.
And I'm not judging her. I mean, she is hot and she is very cute and very smarty. She is Indian, so she has everything that I can only respect her. She is a woman, which is so it's just I only respect her for everything. She tries her best. She's one of the only ones who actually tried to reproduce the double slit experiment with laser beams, whatever. So I'm not detracting from anything she's doing, and she's just repeating what everyone else is saying. But this is just the misconception of science. This is we live in a post-scientific world. We've lost. Science has lost to the ancient religions, to the medieval thinking, to the church. Science has lost. We lost, unfortunately.
5-degree axis to measure the spin in.
Okay, so she's repeating experiments, but she doesn't have a mechanical explanation. There's no mechanical explanation, and she doesn't have a problem. She thinks that a non-mechanical, she's going to just take a non-mechanical explanation and contradict our notion of reality from this non-mechanical theory. It's not a theory. This is not science. I'm not saying it's not. Look, it's the beginning. You're collecting data. You don't have a theory yet. You don't have a mechanical explanation of a quantum phenomenon yet. You need to work at it. It's not going to be easy, but to just give up and run to conclude, well, therefore reality is wrong, that's nonsense. Interesting. Fascinating. Absolutely fascinating. This is very deep, very sad. This is the very sad state of modern science, of modern physics.
What would we normally expect? Well, the 45-degree angle axis is still somewhat pointing in the x direction, so we'd expect that there is some spin in that direction, but a smaller amount than s. We can calculate how strong we think it should be using vectors and get that the new spin should be s on root 2. But what happens when we measure it? Again, every single time we repeat this experiment, the electron will have spin of strength s, but this time it will be slightly more likely to have it in the positive direction than the negative, so that when we take the average of all the results, we get s on root 2. Again, though each individual trial was...
That's good. So that gives you hints that you might be able to explain it. You're in the right direction. So, you're getting some predictions, you're getting some things right, some things make sense, but it's not a mechanical explanation. You're just collecting data. So you still have your work cut out for you still. You cannot just stop midway through a theory and say, that's a theory, a non-mechanical explanation, that's a theory. Let's use that, and our reality goes out the window. No. You have to finish. You didn't finish. You have to finish creating a mechanical theory to explain quantum mechanics. You call it quantum mechanics. I didn't call it quantum mechanics. You called it quantum mechanics. It's got to be mechanical. If it's not going to be mechanical, then you're not done. If it's not going to be mechanical, so you're not in the right field. You go work in something else. In science, we try to build mechanical theories. Science must be mechanical. You can't just stop and say, it's weird. It contradicts reality. Reality goes out the window. No. Not as long as I'm here. I did not expect to make this video. I thought, there must be something deep. There must be something wrong with the math. Wait a minute. What's going on? What is going on? Okay. All right. Everything is okay. 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 I'll get back later. Only today. Okay.
was unexpected. The average
So I thought, Bell's theorem, it really bothered me. It really worried me. I said, wow, how am I going to solve that? That's going to be so difficult to resolve. Because everybody kept saying, Bell's theorem, it contradicts reality, parallel universes, infinite universes, to the non-locality, non-realism. I was like, well, oh my God, how am I going to deal with that? How am I going to deal with that? Who am I to deal with that? With all these geniuses, they didn't resolve it. I'm going to poop my pants. How am I going to deal with it? And you saw me. I sat through and I listened, and I don't understand this, I don't understand that. It makes sense. That, and there you go. There you go. It's all built. This is what happens when you have a non. This is the result of being non-scientific. Oh, okay. Okay. So I was worried. I thought, you know what? I'm gonna go back to sleep. I'm gonna sleep it off. This is too much. I'm never gonna be able to do this. This is I'm biting off more than I can chew. I'm not gonna make it. I'm not gonna make it. I watched stuff yesterday for hours, overnight. This morning, I watched and watched and watched, and everybody was like, yeah, this is, there's nothing we can do about it. This is like bulletproof. There's nothing we can do about this. This is impossible. We cannot defeat this thing. This thing is defeating reality. Okay? So okay, let's assume it is defeating reality. So what? So we go to the many worlds interpretation. But Sutter said, that's no good. That's not an explanation either. How do you explain that the splitting of the universes? Explain the mechanics. The wave, the pilot wave, explain the mechanics. That's also no good. Everything is no good. Copenhagen has the collapse of the wave function. That's also how no one knows how that works. Okay. So all the interpretations have problems. Okay, so it's not like the many worlds is going to solve anything. Okay, so there is no solution. Okay, all right. So I'm not going to get away with anything. So I need to deal with this. This is something that we need to deal with. And the many worlds for me is unscientific. So I'm not going to go with the many worlds. That's a complete violation of intuition. Science has to be intuitive. Otherwise, it's not science, the way I define it. And it's all about me. You have to convince me. It doesn't help me that you are convinced that Einstein thinks something is right. It doesn't help me. I need to think Einstein is right. It's all about me. I am the final judge of what is truth in this universe. In this universe, I am God. Not even God is God. I am God. I am responsible for my life in this universe. I need to know what is true and what is false. I cannot rely on literally anyone, not even God, not Einstein, not the scientific community. I don't care. I don't care. I honestly don't care. Now, if it's a hot chick, like Looking Glass Universe, then fine, it's a hot chick. Then I give her extra credit, but still, and even she says it's weird. So what can I do? She says it's weird, and she says, and it's not a mechanical explanation. This is not a mechanical diagram. There's no mechanics here. These are just, it's not mechanical. I need a mechanical explanation. You need to be able to explain why it's sometimes this and why it's sometimes that, why it's S, why it's not something else. You need to explain every little thing mechanically. You have to. I'll help you. I'm on your side. I'm not going to sit here and laugh at you. But as long as you don't give me a scientific, a mechanical, an intuitive, a simple theory, then you cannot take it, run with it, conclude, therefore, our intuition is incorrect, and declare what? No, you can't.
Result is what we thought.
And I'm incredibly surprised that I'm able to sit here and very comfortably conclude, yeah, they're wrong. They're just all wrong. And I'm right. And Einstein was right. Einstein was right again. I mean, not that he was always right, but in this case, he was in the right, he had the right intuition. It was just intuition. He didn't sit like me and explain. Wait, do I need to respond? Oh, okay. So he wasn't like me sitting comfortably and saying, it's a bore. You are misunderstanding science. This is not about quantum mechanics. This is about the definition of science. So your quantum mechanics is not a scientific theory. It's not complete. You have to complete it. That is what EPR says. It's incomplete. That's all they said. They just said it's incomplete. You have to complete it. This is incomplete. Look, that's all I'm saying. That's all Einstein said. That's EPR. EPR just said that's incomplete. Of course, it's going to create, it might create conflicts with intuition, with reality, with locality. Of course, it's incomplete. As long as it creates these contradictions, it's incomplete. So just complete it. You don't have to give up and say, we'll never make it. No, you have a job. You're getting paid. You should be happy. This is job, what do you call it? This is job security. This is what you're hired to do. So instead of doing what you're hired to do, you abandon your post, you abandon your commitment to the public that hired you, and you just give up, and you say, we're never going to understand it. The conclusion is reality is not real, and reality is not local. And science is not mechanical, and science is not intuitive, and this universe is not rational. Why? All that Einstein said is quantum mechanics is incomplete. That's all. That's all he said. Let's. I want to find. The original EPR paper, because now it's really critical. So in the beginning, I heard EPR, the EPR paper, and I was like, what is Einstein talking about? What are they talking about? Okay, what is this? Kinship? Oh my God. What else? Okay. Everything's fine. What is this white square? Okay, everything's fine. Okay. So let's look at the EPR paper. This is the EPR paper.
Welcome to the 10th video in this series on quantum mechanics. Here we'll explore the radical implications for our understanding of reality arising from experimental violations of Bell's inequality. Throughout this series, we've seen that the bizarre predictions of quantum mechanics.
So these are two good friends. Just to make sure this is clear. So Bohr was a Swiss half Jew. His mom was Jewish. Einstein was, I think, German, Jewish. These two guys were good friends. They enjoyed talking to each other. They probably grew in their knowledge of quantum mechanics more than anyone else ever. Because just by sitting and talking, you become the wisest possible. You become unbelievable. If I could just talk to someone about something, I don't care what, whatever the topic is, very quickly you become the most brilliant brain in the universe vis-a-vis that topic. So this is incredible how they're you can, if this is an actual picture, I wouldn't be surprised. Look at how he's laid back. Obviously he's explaining, and he knows he always had to come back. He never attacked. He always was on the defensive. But Einstein, I think Einstein fell into a logical fallacy that at one point you have to tell your opponent, you have to say, listen, this is not about science, or this is not about quantum mechanics. This is about the philosophy of science. And you guys, you have to agree on what science is. And that's what it was about. It was just about, it was a disagreement. Because they did not talk about the philosophy of science, they could disagree forever, but they never spoke about the definition of science.
Generated considerable debate, most famously between Niels Bohr, who championed the new physics, and Albert Einstein, who, although he played a central role in it,
it's not new physics. It was just nonsense. It was nonsense, and it's still nonsense. If I listen to Looking Glass Universe, and she says it's weird, it's unexpected, and calculate this using trig, society will judge you, but I won't, and I don't know. So she judges it. Something suspicious is happening. So that's okay. That's not new physics. That's just not physics. It's just not physics. There's no new physics. But it's not like it's a disagreement. It's not, he's expressing it as if it's like a disagreement at the philosophical level. No, that has nothing to do with it. It has to do with the very definition of science. If our discussion is causality, so this guy is championing causality and this guy doesn't care about causality, that's not, then at this point Einstein has to say, then, come back when you believe in causality, because that's just an assumption. Causality is an assumption. I'm not going to have a discussion with someone who doesn't assume causality. I don't know what to do with that. I'm not even sharing. I don't know how to have a discussion. I don't know what logic is. I don't know anything unless we assume causality. So you want to tell me this guy believed in causality and this guy did not? That's ridiculous.
championed the new physics, and Albert Einstein, who, although he played a central role in its development, pushed back vigorously in support of classical determinism and causality.
Classical determinism is the assumption. Causality is the assumption. If you end up contradicting classical determinism and causality, then we have nothing to talk about. Me and you were just too different. It's the end of that. That's the end of it. then you're not a scientist. Science is, by definition, causality and determinism. Science is, by definition, a mechanical universe. That's the definition of science. That's the definition of being a rational person. That's the definition of the Enlightenment, of the scientific revolution.
Who championed the new physics, and Albert Einstein, who, although he played a central role in its development, pushed back vigorously in support of classical determinism and causality.
It's like there's a conflict. There's a discussion to be had, whether we should go with classical determinism or what. What's the alternative? What's the alternative to classical determinism? This is such nonsense. It's literal nonsense. So Einstein wanted classical determinism, and Bohr said, "No, we don't need that." So what kind of a universe do you live in? Do you live in a universe where you wake up yesterday? Well, I don't know. So what kind of universe do you live in? What kind of nonsense is this?
The primary source of quantum weirdness is wave-particle duality, is formalized in the wave.
What are you talking about? There's no issue with wave-particle duality, wave function postulate. Everything that we can know about a system is described by its wave function. What? Why do you say that? Wave function is just the data. Wave function is not a theory. What do you mean postulate? What's your evidence that this wave function does anything? So your evidence is that you always get it right? Okay, that's good. But what's the mechanical explanation? You have to have a mechanical explanation. It's nice that you have a function that describes, that gives you good predictions. That's good. I'm not going to complain. I'm not going to say it's bad. 1 second. Oh my God. Oh, one thing is for sure. I did not expect to sit here for hours and lecture the world why Bell's theorem is nonsense. That's the last thing I expected to be able to do. The last thing I expected to do was to sit here and mock Bohr.
Function description of quantum systems.
What?
In the wave function, primary source of quantum weirdness is wave-particle duality.
What do you mean quantum weirdness? What are you talking about? What do you mean quantum weirdness? I don't understand. What the heck are you talking about? What is quantum weirdness? I don't even know what you're talking about. What is quantum weirdness? What is that? Define quantum weirdness. So I was listening to this morning and was like, wow, this is going right over my head. Wow, I'm never going to be able to understand any of this. But now that I'm listening to it, this is utter rubbish. This is atrocious, as John says. This is unacceptable. This guy's out of control. This guy's completely out of control. This is immediate downvote. What else did I say? Conservation of momentum is actually not required. I don't need to say that. Heisenberg uncertainty is just a Fourier analysis. It is derived from classical wave theory. That's fine. But the first one, conservation of momentum, is actually not required. I don't know if these are true. I don't know. So let's edit this. So instead, I'll tell you something else. So 036. O:36. So what did I want to say? What did he say?
Is formalized the primary support of classical
quantum
determinism and
weirdness.
causality. The primary source of quantum weirdness is wave-particle duality.
What are you talking about? What is quantum weirdness? When was this video? This is from 10 years ago. Quantum weirdness. What are you talking about? What do you mean? What is quantum weirdness? Is that a scientific term? But I shouldn't even say that. It's just, what's my position? What is my position? Let's just gonna remove this comment. We're gonna remove this comment as well. Back and I'll attack precisely where I think it's wrong.
Duality is formalized in the wave function description of quantum systems. In 1935, Einstein, Podolsky, and Rosen published a paper titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?"
That's it. That's it. That's basically it. That's all they're saying. And Bell's theorem proves this correct. Literally. 051. Can quantum mechanical description, blah, blah. Can quantum mechanical be considered complete? Can quantum mechanical be complete? Oh, the question mark is inside. Good question. Bell's theorem literally proves EPR to be correct. So the proof by contradiction assume quantum mechanics is complete. Quantum mechanics leads to contradiction with our reality. Done. That's the proof. That's it. That is literally the proof. That is literally the proof. I have nothing to add. There's nothing to add. If your assumption leads to a contradiction with reality, we're done. Obviously, quantum mechanics is incomplete. Let me know if I can help you, if you have any questions. That's it. I don't know what else to say. We're done. That's it. We're done. It's very simple. Very straightforward. There's zero complications. Let me know if I can assist you further. So usually we say wine. Not this wine. Drink? No. There it is. Cheers. Why is there two of them? That's it. Can quantum mechanical be considered complete? Can quantum mechanical be considered complete? Good question. Bell's theorem literally proves EPR to be correct. Proof by contradiction. Assume quantum mechanics is complete. Quantum mechanics leads to a contradiction with our reality. Therefore, quantum mechanics is not complete. Done. That's it. Have a great rest of your evening. We're done. In a complete theory, there is an element corresponding to each element of reality. A sufficient condition for the reality of a physical quantity is the possibility of predicting it with certainty without disturbing the system. In quantum mechanics, in the case of two physical quantities described by non-commuting operators, the knowledge of one precludes the knowledge of the other. In either one, the description of reality given by the wave function in quantum mechanics is not complete. Or two, these two quantities cannot have simultaneous reality. Consideration of the problem of making predictions concerning a system on the basis of measurements made on another system that had previously interacted with it leads to the result that if 1 is false, then 2 is also false. One is thus led to conclude that the description of reality as given by a wave function is not complete. I'm not sure what they say, but I mean, I think they're also, this, you don't even need Bell. This is the point. The proof is done here. That's it. The proof is done. There's nothing to add to this. Bell didn't prove them wrong. Bell proved them right, but you don't even need that. They were all from Princeton, so they were all working together.
They argue that although quantum mechanics is a very successful description of nature, it cannot represent a final, complete theory. In a complete theory, they asserted, there is an element corresponding to each element of reality.
It has to be completely mechanical. If it's not completely mechanical, you're not done. You haven't finished your job. Finish your job.
They gave the following working definition.
You can't give up. You can't say, oh, I'm done. No, you're not. You don't say when you're done. You're not done. I'm not saying you're far from done, but you're not done.
A sufficient condition for the reality of a physical quantity is the possibility of predicting it with certainty.
Absolutely. It's got to be a mechanical. If it's not mechanical, go back and keep working at it. You'll get it.
Without disturbing the system. They then presented a thought experiment designed to show that quantum mechanics cannot be a complete description of reality. A simplified version of their argument is as follows. Suppose at the origin of the x-axis, some event emits two identical particles. One travels to the right with momentum p1 in position x1, and the other to the left with momentum p2 in position x2. If the total momentum of the system was initially zero, then to conserve zero momentum, p2 would have to be the opposite of p1, so that their sum is zero. Because the particles are identical, opposite momentum means opposite velocity. So position x2 would at all times be the negative of position x1. Now, quantum mechanics says that the position and momentum of particle 1 cannot both be real, according to the EPR definition, because of the uncertainty principle. If we shrink one uncertainty to zero, either delta x1 or delta p1, then the other uncertainty has to grow to infinity so that their product is never less than Planck's constant. According to quantum mechanics, if the position of a particle is real, then its momentum cannot be, and vice versa. Now, suppose we make a measurement on particle 2. If we measure its position, x2, then due to the relationship between x1 and x2, we can predict x1 with certainty without having disturbed particle 1. So, x1 becomes real. If we instead measure the momentum, p2, then we can predict p1 with certainty, again without having disturbed particle 1. So p1 becomes real. In this experiment, reality for particle 1 depends on measurements made on particle 2, and these particles can be arbitrarily far apart. EPR argue that no reasonable definition of reality could be expected to permit this. One is thus led to conclude the description of reality as given by a wave function is not complete. In previous videos, we've described how in quantum mechanics...
It's still going over my head, but intuitively, I don't know what proof he went through.
Measurements are formally represented by applying operators, which we denote with a little hat or caret mark. If applying two operators in a different order produces a different quantities in 2 are both momentum, the mechanics permits the measurement of x2 or p2 allows us to predict with certainty. No doubt about it, the EPR paradox forces us to conclude that either quantum mechanics is incomplete or our concept of reality needs a radical revision. EPR were clearly in favor of the former. A few months later, Niels Bohr published a response under the same title in which he defended quantum mechanics and came down on the radical revision side of the fence.
Radical?
He argued that the wording of the above-mentioned criterion of physical reality proposed by Einstein, Podolsky, and Rosen contains an ambiguity as regards the meaning of the expression without in any way disturbing a system. By the end of this video, we'll hopefully have a good understanding of this ambiguity. The gist of it is that the necessity of discriminating in each experimental arrangement between those parts of the physical system considered which are to be treated as measuring instruments and those which constitute the objects under investigation may indeed be said to form a principal distinction between classical and quantum mechanical description of physical phenomena. Bohr emphasized the finite and uncontrollable interaction between the objects and the measuring instruments. As we've seen throughout this series, in quantum mechanics we've reached a limit in which the very act of measurement can change the properties of the object being measured. In light of these considerations, Bohr claimed that we are forced into a final renunciation of the classical ideal of causality and a radical revision of our attitude towards the problem of physical reality.
Okay, then that's all I need to know. If a final renunciation of the classical ideal of causality. He calls causality an ideal. And a radical revision of our attitude towards the problem of physical reality. The problem of physical reality? All right, so this is nonsense. This is literal nonsense. This is just literal nonsense. A final renunciation. I don't need to hear anything else from a person that says he wants to renunciate classical ideal of causality. I mean, what, you don't need to tell me anything else. What is it, 657? This is Bohr. That's how you spell Bohr? Renunciation of the classical ideal of causality. So let me understand this right. So Bell proved EPR is wrong, are wrong, because EPR is right. Oh my god, this is such nonsense. By definition. It's by the definition of the word nonsense. How do you spell Bohr? Yeah, that's how you spell Bohr. Renunciation of the classical ideal of causality. So Bell proved EPR are wrong because EPR is right. Oh well, this is absolute nonsense by definition of nonsense. I don't know what else to say. This is complete garbage.
This is where things more or less stood for about 30 years. People were primarily concerned with applying quantum mechanics in the laboratory.
So basically, Bohr admitted to be wrong.
And the real world.
Bohr admitted to not understand reality, science, nothing. I mean, he's just living in some fantasy universe, completely detached from reality, literally.
This issue, like the Schrödinger's cat paradox, was largely seen as a matter of philosophical interpretation without practical consequences. But it turns out that the debate can be settled experimentally. In 1964, a paper appeared titled On the Einstein-Podolsky-Rosen Paradox, written by John Bell.
Paradox? It's not a paradox. They made fun of quantum mechanics.
We're going to follow a simple version of Bell's argument in which we'll, 1.
He's going to prove them correct! Oh, the last thing I expected to conclude is he proved EPR to be correct. I thought there's no way this is gonna wake me up. There's no way this is gonna brain drain me. This is going to put me to such good sleep. This is so boring. There's no way I can figure this out. And instead, this is just more nonsense. Just more nonsense. Literal nonsense. People denying reality. What? Well, what do you want me to say to that? Are you a chick with big boobs? No. Okay, then get back to work. If you're a chick with big boobs, you can say whatever you want. I'll worship you. I'll do whatever you want. I don't care what you say. You can say whatever you want. Reality is not real. Up is down, down is up, right is left. Whatever you want, you can say. 2 plus 2 is 4, and it's not 4. Fine, it's whatever you say. But you're not a chick. I'm not going to care for what you say. Either you make sense or get back to work until you make sense. Your job is to make sense. You're paid. You're getting paid to make sense. You're not a chick. What a joke. What a complete joke. What a disaster. This is a complete disaster.
Define local reality. 2, generate falsifiable predictions based on that definition. And 3, test the predictions experimentally. What do we mean by local reality or local causality, or for short, just locality?
Oh, for short, causality.
The ultimate goal of physics is nothing short of a complete description of the totality of existence. Now that's a pretty tall order.
I wouldn't say that. You're skipping the most important, crucial steps. That's not
A complete description of the totality of existence.
No. It's got to be a simple, mechanical, causal explanation. Got to be reproducible, the rest of it. But it's got to be simple, intuitive, mechanical. That's explanation. That is science. You don't have that, get back to work. And come back when it's intuitive, simple, mechanical, causal. If it's not that, I don't care. It's not science. I don't care. It's woo-woo. It's voodoo. I don't want to hear it. If I want to hear woo-woo, I'll get a chick. I'll sit and talk to a chick about all the woo-woo in the universe. I'm not going to hear that from a paid scientist.
Now that's a pretty tall order. In principle, everything in the visible universe interacts gravitationally and electromagnetically. If not, we wouldn't be able to see distant galaxies. But there is no way we could function or make progress scientifically if we continuously had to consider the totality of existence. In practice, we need to be able to say,
I don't even know what he's talking about, the totality of existence. I mean, obviously, when science is not going to figure out the beginning of everything, that's out of the question. So we don't need to deal with that. We cannot. We know the limits. So there's no point in talking about the beyond the limits. Science has a job. It's to explain natural phenomenon, one step at a time. Better than yesterday, as Coach Greg says. That's all. It's windy outside. I gotta take care of stuff.
look, here's a little piece of the universe. We'll call it chair.
Exactly. You start with a chair. Complicated enough. There's enough complications in a chair.
The chair has certain properties we can measure and understand independently of what's going on in, say, the Andromeda galaxy. And here's another little piece of the universe we'll call a frying pan. We can also characterize its properties. If we put the frying pan on the chair, we can describe the interaction of the two objects without having to account for, say, the position of Pluto in its orbit. So we can think of a particle, or more generally an object or a system, as existing in a limited region of space at a given time. We assume that the particle has a state x. This could include things such as mass, charge, momentum, and so on. For a complicated object, it would include a description of all the atoms making up the object and the chemical bonds between those and so on. It's not necessary that we actually know the complete state, only that it exists in principle. All measurable properties of the object are assumed to be uniquely determined by the state x. We measure properties of the particle by performing experiments in a local environment we'll call our laboratory. The principle of locality assumes that in addition to the state of the particle, these experimental results depend only on the local environment in the laboratory during the experiment. Now, a remote event, say a distance d away, can certainly have an effect on our experiment, but it does so by producing some disturbance which propagates through space at no faster than the speed of light. This disturbance can eventually enter the laboratory where it becomes part of the local environment during the experiment. So it's still true that the experimental results depend only on the local environment. The distant event can have no effect on the experiment in less than d or c seconds. In particular, it cannot instantaneously influence our experiment. Now we're ready to describe a generic experimental setup which, under our assumption of locality, leads to Bell's inequality. Suppose we take a particle in the state x and subject it to an experiment with two possible outcomes. We'll call this test A and label the outcomes as pass and fail. We have a second test B and a third test C. Under the assumption of locality, the results of these three tests depend only on the local experimental conditions and the state x of the particle. There are 8 possible outcomes of these 3 tests. Using 0 and 1 to represent fail and pass, we can make a table listing all possible outcomes of the 3 tests, and there are only 8 possibilities. Under locality, we assume that a given state x corresponds to one and only one row in this table. A particle in the same state x has to produce the same experimental results. If 2 particles produce results corresponding to different rows of this table, they cannot be in the same state. Now consider a situation where the particle passes test A and fails test B. We can label this as A, B bar, A and not B. That is, A equals 1 and B equals 0. There are 2 rows in our table for which A equals 1 and B equals 0. Now consider a situation where the particle passes test B and fails test C, B and not C. There are 2 rows where B equals 1 and C equals 0. Finally, consider passing A and failing C, A and not C. There are 2 rows where A equals 1 and C equals 0. Notice that, as indicated by these red lines, whenever A and not C occurs, either A and not B or B and not C must also occur. There are no rows in our table for which A and not C occurs, but one of the other 2 situations does not. Suppose we took a large number of particles in random states x and subjected them to these 3 tests. We have counters which keep track of the number of times A and not B, B and not C, or A and not C occur. Then the number of times that A and not B occurs, plus the number of times that B and not C occurs, would have to be greater than or equal to the number of times that A and not C occurs. Because, as indicated by the red lines, the last number cannot increment without one of the other 2 also incrementing. However, it is possible for one of the first 2 counters to increment without incrementing the third. There are 2 rows in the table where A and not B, or B and not C occur, but A and not
I'm not following what the heck he's talking about.
C does not. Therefore, we have an inequality. The left side is greater than or equal to the right side. Now, the number of times an event occurs in a large number of experiments is simply a measure of that event's probability. So we have that the probability of A and not B, plus the probability of B and not C, is greater than or equal to the probability of A and not C. This is Bell's inequality. Alternately, we can illustrate Bell's inequality using a Venn diagram. Suppose the state x of a particle corresponds to a position on the screen. If that's inside the red circle, then the particle will pass test A, while if it's outside, it will fail. Likewise for the test B and test C circles. The region corresponding to A and not B is inside the A circle and outside the B circle, outlined here in white. The B and not C region is outlined in yellow, and the A and not C region is outlined in magenta. The magenta region falls completely within the white and yellow regions, but there are parts of the white and yellow regions outside the magenta region. So the area and probability of the white region plus the area and probability of the yellow region is greater than or equal to the area and probability of the magenta region. However derived, the beauty of Bell's inequality is its simplicity and generality. All we need are a source of particles and 3 pass-fail experiments. Bell's inequality is a straightforward logical deduction from the fundamental assumptions of locality. We've assumed that a given particle exists in a definite physical state x, and that the results of an experiment performed on that particle are determined by this state and the local environment of the experiment. If Bell's inequality is violated in any experiment, it must mean that our assumptions of locality are wrong.
Okay, whatever. All right. I think I'm done. I don't have I don't know what else to say. Not I don't have to understand everyone's explanation of Bell's. I understood some of what they're saying. There's nothing to prove. Einstein proved Bohr wrong. That's the end of it. There's nothing left to say. Bell, if he proved anything, it's that Einstein was right, is that quantum mechanics leads to a contradiction of reality. That's exactly what Einstein said. So you contradict. Okay, so quantum mechanics leads to contradiction with reality. Okay, so it's incomplete. Done. Thank you, Bell, for stressing that Einstein was right. That's it. And I don't know what anybody else, what anyone is talking about. All that Einstein said is quantum mechanics is incomplete. It's not a complete. At the current state, it creates contradictions with reality. So it's incomplete. It's not a good theory. We're not done. It's not like anyone actually disagrees with Einstein. Everyone agrees with Einstein because there's so many interpretations. Why do you get so many interpretations? Because each and every one of them is incomplete. They lead to contradictions. So of course Einstein was right. Of course everyone keeps working on quantum mechanics. What is even the disagreement? Of course Bohr was wrong. I don't know what to say. That's it. What is ether from 6 years ago? A history of the debate about the substance of the universe by Jeff Yee. News roundup. Let's go listen to the news roundup. Oh, it's upcoming. Okay. Anyway, I was worried that it's going to be impossible to understand, and instead it's not trivial to understand because I'm not sure what Bell is even trying to say. I mean, Bohr literally says nonsense. Literally nonsense. He says, "Oh, causality. We have to forgo the notion of causality." Okay, I don't need to debate Bohr. Bohr debated Bohr, and the debate is over. Bohr doesn't like causality, locality, realism. All right, I'm done. I have nothing left to say to Bohr. There's nothing left to say. We're done. Even Einstein didn't need to write. Einstein wrote the paper, the EPR paper, and Bohr responded, "Yeah, Einstein, you're right. We're done." Yeah, that's it. The funniest thing would be to discover that Bohr wrote it as an admission, because that's basically what it is. Anyway, I don't know what else to say. If anyone proves that quantum mechanics leads to a contradiction with reality, then that's a proof for EPR. That's exactly what EPR is arguing. That's literally what EPR is arguing. Quantum mechanics is incomplete. Does anyone think quantum mechanics is complete? Is there anyone roaming the universe thinking quantum mechanics is complete? Are they happy with quantum mechanics? Point them out to me. All I hear is people complaining about quantum mechanics, how they don't understand it, including Feynman. Even he says you cannot understand it. So you call that complete? A theory that you don't understand, that's the definition of complete, that you don't understand it? Okay, that's fine. That's fine. All right, everyone. It's been 4 hours. I think it's a good video. I think it's a pretty good video. I probably beat the horse to death multiple times, and it's the same horse. It's not like it's a new day, new horse. It's always the same horse. How's my audio? I hope my audio is good. Yeah, it's good audio. It's all good. Yeah. Okay. The Aaron Brooks show is starting. I gotta go listen to the news. All right, everyone. Thank you very much. Good stuff. See you next time.